24 billion kilometers from where you're sitting right now. Something is moving through the darkness. It has no fuel left to stop, no way to turn around, and nobody alive will ever see it again. It is a machine built with 1970s technology, running on just 69 kilobytes of memory, less than a single low-res photo on your smartphone, that somehow changed everything we knew about the universe. And on its long, silent journey to the edge of the solar system, it found 9 discoveries nobody was prepared for. Discoveries that forced the most brilliant scientific minds on Earth to stop, sit down, and completely rethink the world we live in. One revealed an invisible force protecting all life on Earth. Another captured an actual sound coming from the darkness between stars. And the further the Voyager spacecraft traveled from home, the more wrong our understanding of the universe turned out to be. Stay with me, because every single discovery gets more unsettling than the last. And that silence, that's the most haunting part. Before we dive in, if you love exploring these kinds of deep space videos, a simple like or subscribe really helps this channel reach more curious minds like yours. Now, let everything soften, and together we drift into space. Right now, as you watch this, there are 2 human-made objects moving through interstellar space, not orbiting, not slowing down, not approaching anything we have named or mapped, just moving, outward, into the dark between the stars. They were built in the 1970s, with less computing power than the chip inside a modern greeting card. They were designed for a mission that was supposed to last 5 years. 5 years, and then silence. That was the plan. But the universe had other ideas. To understand what these spacecraft found at the edge of the solar system, what they revealed about the boundary between our cosmic home and everything beyond it, we first have to understand what they were built to do and what they were never supposed to become. The year is 1977. America has just celebrated its 200th birthday. The first personal computers are appearing in hobbyist magazines, soldered together in garages, and a small group of scientists at NASA's Jet Propulsion Laboratory in Pasadena, California, are quietly preparing to take advantage of something that happens once every 175 years. 175 years. That is roughly the same span of time that separates us from the American Civil War, an entire era of human history compressed into a single orbital coincidence. Because once every 175 years, the 4 great outer planets of our solar system, Jupiter, Saturn, Uranus, and Neptune, arrange themselves in a rare geometric arc, and when they do, a spacecraft launched from Earth can use each planet's gravity like a slingshot, gaining enormous speed from each one in sequence, without burning a single drop of additional fuel. This technique is called a gravity assist. Picture rolling a ball toward the edge of a spinning merry-go-round. The ball catches the rim and gets flung outward, faster than it arrived, carrying away energy borrowed from the spinning structure itself. A spacecraft passing close to a massive planet does something mathematically identical. The planet's gravitational field pulls the craft in, bends its path, and hurls it onward with added velocity. The planet loses an almost immeasurably tiny fraction of its own orbital energy. The spacecraft gains enough speed to reach the next target in a fraction of the time it otherwise would. That window opened in 1977. It would not open again for another 175 years, long after every person involved in the mission would be gone. The opportunity was too extraordinary to miss, so NASA built 2 spacecraft. Voyager 2 launched first, on August 20th, 1977. Voyager 1 followed 16 days later, on September 5th. They were sent on different trajectories. Voyager 2 on a longer, slower arc, designed to visit all 4 outer planets in sequence. Voyager 1 on a faster, more direct path optimized for close encounters with Jupiter and Saturn, and specifically with Saturn's moon Titan, which scientists suspected might harbor a thick atmosphere unlike anything else in the solar system. The mission was called the Voyager Interplanetary Mission. That name is everything. Interplanetary. Between planets, not between stars, not beyond the solar system. The goal was specific, defined, and finite. Scientists wanted images, measurements. They wanted to understand Jupiter's storms, Saturn's rings, the distant ice giants that our telescopes at the time could barely resolve as anything more than pale smudges of light. The spacecraft carried cameras, magnetometers, instruments that measure magnetic fields, plasma detectors that could sample the charged particles flowing outward from the Sun, and cosmic ray sensors to detect high-energy particles streaming in from deep space. They were equipped, in short, to do a job and come home in the form of data. And engineers were honest about the timeline. These spacecraft were designed to operate for roughly 5 years, long enough to complete the planetary tour, long enough to transform our understanding of the outer solar system, and then, almost certainly, to go quiet. The kind of silence that follows a rocket launch, after the roar fades and the crowd exhales, is unlike any other quiet in the world. Some of the engineers who built Voyager expected to retire before the mission was over. Some of them did. When Voyager 1 swept past Jupiter in March of 1979, just 18 months after launch, the images it returned were unlike anything ever transmitted to Earth. Active volcanoes on Io, one of Jupiter's moons, the first active volcanoes ever observed beyond Earth. A great red spot that turned out to be a storm system larger than our entire planet, churning without pause for centuries. Scientists gathered around the data terminals at JPL, watching these images download line by line onto their screens, and simply went quiet. The solar system was not the frozen, silent museum they had imagined. It was dynamic, alive, stranger than anyone had predicted. Saturn followed. In November of 1980, Voyager 1 swept through the Saturn system and sent back photographs of its rings in extraordinary detail. Billions of pieces of ice and rock, ranging from tiny dust grains to objects the size of houses, all orbiting in razor-thin bands of precise geometry. And there was Titan, Saturn's largest moon, wrapped in a thick orange haze so opaque that Voyager's cameras could not penetrate it. But the instruments confirmed something remarkable. Titan had an atmosphere denser than Earth's. Scientists could not see the surface, but they could feel through the data that something extraordinary was waiting there. After Saturn, Voyager 1's trajectory bent sharply northward, carrying it out of the plane of the solar system and away from the remaining planets. Its planetary mission was complete. Voyager 2 continued. Uranus in January of 1986, Neptune in August of 1989, 12 years after launch, 3 billion miles, nearly 5 billion kilometers traveled, 4 planets visited, dozens of moons photographed for the first time in human history, a solar system revealed in detail no living eye had ever seen. The cameras were powered down to conserve energy. The planetary mission was declared complete. The spacecraft had done what they were built to do. The 5-year mission had stretched to 12, and now it was over. That was supposed to be the end of the story, but the spacecraft kept going, and this is where something remarkable happened. Not in the cosmos, but in a conference room at NASA. Scientists looked at the Voyager probes, still transmitting, still drawing power from their nuclear generators, their instruments still reading, and they asked a question that had no precedent. What if we do not turn them off? What if, instead of simply tracking these machines as they fade toward the edge of detection, we keep listening? What if we point them not at planets, but at the boundary itself? In 1990, NASA officially established what became known as the Voyager Interstellar Mission. The goal was no longer planetary science, the goal was the edge. The true outer boundary of the solar system, a region that no instrument, no model, no theory had ever directly sampled in the history of science. Picture this, a ship that set out to cross a lake. It crossed the lake, it mapped every island, every current, every depth, and then, When the crew looked up from their charts, they realized the lake connected to a river. The river opened into an ocean, and the ocean stretched far beyond anything they had prepared to find. So instead of turning back, they kept sailing. That is what happened to Voyager. As of today, Voyager 1 is more than 15 billion miles, roughly 24 billion kilometers from the Sun. To feel what that means, if you try to cover that distance in a car moving at a steady 60 miles per hour, highway speed, it would take you approximately 28,000 years to arrive. 28,000 years ago, human beings were painting animals on cave walls in southern France. We had not yet invented farming. We had no writing, no cities, no wheels. We were in the Stone Age. That is the distance this spacecraft has covered. And Voyager 1's radio signal, travelling at the speed of light at 186,000 miles per second, the fastest speed that physics allows, still takes more than 23 hours to reach us, one way. When mission controllers send a command to Voyager 1 today, they wait more than 46 hours for the round trip, longer than most people sleep in a full week just to hear back from their own machine. We are now approaching a haunting milestone. In late 2026, Voyager 1 will reach a distance of one full light day from Earth. A radio signal, the fastest thing in the universe, will finally take an entire 24-hour cycle just to bridge the gap between us and our most distant messenger. That is the spacecraft you are going to follow today, built with technology your grandfather could have repaired with a soldering iron, designed by people who are now in their 70s and 80s, or gone, still moving, still transmitting, still sending back data from a place no human object has ever reached before. What the engineers built in 1977 was a planetary explorer. What they accidentally created was humanity's first interstellar probe, and the mission they never planned, the one born not from design but from stubbornness, from curiosity, from the simple refusal to stop listening, turned out to be the most scientifically significant mission NASA has ever flown. Because what Voyager found as it crossed toward the edge of the solar system, and then beyond it, shattered every model scientists had built about what that region would look like. The edge of the solar system was not empty. It was not quiet. It was not the clean, simple boundary anyone had drawn on paper. It was a frontier, dynamic, turbulent, layered with phenomena that no instrument had ever sampled, no theory had fully predicted, and no scientist had fully imagined. 9 discoveries, each one more unexpected than the last, each one rewriting something we thought we understood. But to understand what Voyager found there, we first need to understand what scientists believed the edge would look like, because the story of every one of these discoveries begins in the same place, with a model that seemed completely airtight, a prediction built on decades of careful reasoning, a boundary drawn with confidence on every map of the solar system ever printed, and a question that sounds almost embarrassingly simple until you try to answer it. Where does the solar system actually end? The edge of the solar system should be easy to find. That is what most people assume. The Sun is in the center. The planets orbit around it, and somewhere out past the last planet, the solar system simply ends, like the edge of a table, a clean line, a clear boundary. Beyond it, empty space. Before it, our home. It is a completely reasonable picture. It is also completely wrong. Here is the problem that scientists have wrestled with for decades, and that Voyager was eventually sent to resolve, not with a camera, but with its instruments reading the invisible fabric of space itself. The solar system has no wall, no fence, no visible edge. If you were traveling outward from the Sun, there is no moment where you would see a line across space and think, here it ends. The darkness on one side looks identical to the darkness on the other. The stars do not change. The cold does not shift. Nothing marks the transition in any way your eyes could detect. So the question becomes genuinely difficult. Not philosophically difficult, scientifically difficult. How do you define the boundary of something that has no surface? And the answer, it turns out, lies not in what you can see, but in what the sun is constantly doing, invisibly, relentlessly, in every direction at once. The sun is not a static object, it is an engine, and like any engine, it releases material, not just light and heat, but an actual physical stream of particles, a continuous flow of electrons and protons blasted outward from the sun's outer atmosphere at extraordinary speed. This is called the solar wind. It is not a metaphor, it is not an analogy, it is a real wind, a stream of charged particles moving outward from the sun in every direction at once, like a breath exhaled continuously into space, never stopping, carrying the sun's influence with it as it travels. The solar wind moves at roughly 250 to 500 miles per second. That is 400 to 800 kilometers per second. To feel that speed, a commercial airliner flies at about 10 miles per minute. The solar wind is moving thousands of times faster than that. If the solar wind were carrying a passenger aircraft, that plane would cross the entire width of the continental United States, roughly 2,800 miles, in just over 10 seconds. A warmth you cannot feel, travelling at a speed you cannot outrun. This wind has been blowing since the sun formed, roughly 4.5 billion years ago. It has never stopped. It does not stop at the planets. It does not stop at the orbit of Neptune, the outermost planet in our solar system, located about 2,800 million miles, approximately 4.5 billion kilometers, from the sun. It keeps going, past Neptune, out into the vast dark beyond, losing speed and density as it spreads, but never ceasing entirely. And as it travels, it pushes outward against something, because the space between the stars is not truly empty either. This is the other half of the equation. The region between star systems, what astronomers call the interstellar medium, is not a perfect vacuum. It contains a thin, cold gas of hydrogen and helium atoms, along with magnetic fields and high-energy particles called galactic cosmic rays that stream through the galaxy from distant violent events, exploding stars, colliding neutron stars, the churning engines at the hearts of galaxies. This interstellar medium is extraordinarily thin. Picture this. If you took the entire atmosphere above your head, compressed it, and spread it evenly across a volume of space the size of a football stadium, the resulting density would still be millions of times denser than the interstellar medium. It is almost nothing. Almost. But almost nothing at large enough scales becomes something significant, because the solar wind, flowing outward from the sun at hundreds of miles per second, is constantly pushing against this thin interstellar gas, and the interstellar gas is constantly pushing back. What this creates, and this is where the picture becomes genuinely extraordinary, is a boundary region, a zone where these two forces meet and press against each other, and the region enclosed within that boundary, the vast bubble of space dominated by the sun's wind, stretching in every direction from the sun, has a name. It is called the heliosphere. The heliosphere. Think of it as the sun's domain, the region of space where the sun's influence carried outward by its wind is still powerful enough to hold the interstellar medium at bay. Everything inside the heliosphere is, in a meaningful sense, under the sun's protection. Everything outside it belongs to the galaxy. Now here is where the scale of this becomes something you need to sit with for a moment. The distance from the sun to Earth, the familiar, well-travelled distance that defines our seasons, our days, our entire sense of cosmic scale, is roughly 93 million miles, or 150 million kilometers. Scientists call this one astronomical unit, or 1 AU for short. 1 AU is our basic yardstick for measuring the solar system. The heliosphere, based on early theoretical models, was expected to extend to somewhere between 100 and 150 astronomical units from the Sun. 100 astronomical units. That means the heliosphere is roughly 100 times the distance from the Earth to the Sun, and the Earth to the Sun already takes light 8 minutes and 20 seconds to cross. Think about that distance on a more human scale. If the Sun were the size of a basketball sitting in the center of a large city, say, in the middle of Times Square in New York, the Earth at the same scale would be a single peppercorn about 90 feet away. Neptune, the outermost planet, would be roughly half a mile from the basketball, and the edge of the heliosphere, the bubble the Sun creates around itself, would be somewhere between 2 miles away. 2 miles from a basketball in Times Square. That is the size of the Sun's protective domain, scaled to something you can walk. And beyond those 2 miles, in every direction, the interstellar medium, the galaxy, everything else. Here is what scientists believed before Voyager arrived to test these ideas directly. The theoretical framework for the heliosphere was built primarily in the 1950s and 60s. In 1958, a physicist named Eugene Parker at the University of Chicago published a paper predicting the existence of the solar wind. And this is worth pausing on, because at the time, Parker's paper was considered so controversial, so unlikely, that it was initially rejected by the journal he submitted it to. The reviewers thought the idea was wrong. The idea that the Sun continuously exhaled a supersonic wind of particles in all directions seemed, to many physicists of the era, physically implausible. Parker was right, completely and definitively right. Spacecraft confirmed the solar wind's existence just a few years later, in the early 1960s. And with that confirmation, the theoretical picture of the heliosphere began to take shape. Scientists built models. They used what they understood about the solar wind's speed and density, combined with what they knew about the pressure of the interstellar medium, and they calculated where these two forces should balance. They expected the solar wind to slow as it travelled outward, eventually reaching a distance where it could no longer push against the interstellar gas, and there, at that boundary, the heliosphere would end. The models were precise. They produced specific predictions. They assigned numbers to the location of various features within and around the heliosphere. Teams of scientists built careers around these calculations. The models were tested, revised, tested again. By the 1980s and 90s, there was broad scientific consensus about the basic structure of the heliosphere and roughly where its boundaries would be found. The science was settled, or so it seemed. The solar wind was real. That was confirmed. The heliosphere was real. That was understood. The models were sophisticated. They had decades of refinement behind them. Every theoretical tool available pointed to the same basic picture. And then Voyager started sending back data from the outer solar system, and the picture began to crack. Here is what the models predicted Voyager would find as it travelled outward. A smooth, relatively predictable journey through declining solar wind pressure, a gradual transition, a boundary that, while complex in detail, would behave roughly as the equations described. Scientists expected to see the solar wind slow predictably. They expected the magnetic field carried by the solar wind to weaken steadily. They expected the intensity of galactic cosmic rays, those high-energy particles from deep space, to rise smoothly as Voyager approached and then crossed the outer boundary. Clean, ordered, logical, the behavior of a system that science understood. But here is the thing about the universe. It does not read the models. And what Voyager actually found, beginning with the first major discovery that arrived not as a dramatic announcement, but as numbers changing on a data screen at JPL, was a solar system boundary that was nothing like anyone had predicted. Not slightly different, not a modest revision to the existing picture, profoundly, structurally, fundamentally more complex than any model had anticipated. And this matters to you, not as an abstract scientific curiosity, but because the heliosphere is the reason life exists on the surface of this planet. Right now, the bubble the Sun creates around itself is deflecting a significant portion of the galactic cosmic rays that would otherwise be streaming through Earth's atmosphere. Those particles, if they arrived at Earth in their full, unfiltered intensity, would damage DNA, increase cancer rates, and alter the radiation environment of the planet in ways that would make Earth less hospitable to complex life. The heliosphere is not just a scientific boundary, it is a shield, and understanding where it ends, how it behaves, and what forces shape it is not an abstract academic question. It is a question about the conditions that make our world livable. So the question scientists were asking, where does the solar system end, turned out to be a far richer question than it first appeared. It was not a question about a line on a map. It was a question about a dynamic, living boundary, one shaped by the Sun's output on one side and the galaxy's interstellar environment on the other. A boundary that breathes, that shifts with the Sun's activity cycles. That is not a wall, but a negotiation, constant, invisible, and absolutely essential to the conditions of life in this part of the galaxy. Voyager was the first instrument humanity ever sent to cross that boundary and measure what it found there. And the discoveries it made, 9 of them, each more unexpected than the last, begin not with the boundary itself, but with what lies just inside it. Because before Voyager could reach the edge of the heliosphere, it first had to travel through it. And what it found inside the Sun's protective bubble, the structure and function of the heliosphere itself, was the first of 9 revelations that would force scientists to rewrite their understanding of the solar system from the outside in. This is shocking discovery number 1, and it begins with a question of what exactly this bubble is made of, and why, without it, the planet you are sitting on tonight might look very different than it does. Shocking discovery number 1. Not at the edge of the solar system, not beyond the planets. Right here, surrounding everything we have ever known, stretching billions of miles in every direction around the Sun, is a structure so vast, so fundamental to the existence of life on Earth, that scientists are still working to understand its full shape and behavior today. Voyager did not find it by arriving somewhere new. It found it by measuring what was already there, all around it, and revealing for the first time exactly what that structure does. We established that the Sun exhales continuously, a relentless stream of charged particles, the solar wind, flowing outward in every direction, carrying the Sun's magnetic field with it as it travels. And we established that this wind does not simply dissolve into the galaxy. It pushes outward against the thin gas and magnetic fields of interstellar space until the two forces reach a standoff, and the region enclosed by that standoff is the heliosphere. But knowing the heliosphere exists, in theory, is very different from understanding what it actually does. Think of it this way. Imagine you have lived your entire life inside a greenhouse. The glass walls are completely transparent. The air feels the same. The temperature is controlled. You have never questioned what the walls are for. They are simply there. And then one day, someone removes a single pane, and you feel, for the first time, exactly what was being held back from outside. That is what Voyager's measurements began to reveal. Not just that the heliosphere exists, but what it is protecting us from. And the answer, when it arrived through the data, was sobering. The heliosphere is not a simple bubble with a clean outer wall. It is layered, a series of nested regions, each with its own character, each playing a different role in the overall structure. Voyager's instruments, as the spacecraft travelled outward across decades, sampled each of these layers in sequence, and what they measured built a picture of a structure that is, in the most precise scientific sense of the word, remarkable. At the centre is the Sun itself, the source and engine of everything. Surrounding it, extending outward in all directions, is the solar wind, that continuous flow of charged particles we discussed. For most of its journey, the solar wind is supersonic. It is moving faster than the speed at which pressure waves can propagate through the plasma, the electrically charged gas it travels through. Supersonic means, specifically, faster than sound in that medium. In the solar wind flows at roughly 250 to 500 miles per second, 400 to 800 kilometers per second, while the relevant sound speed in that plasma is far lower. So for billions of miles in every direction, the solar wind is a supersonic river flowing away from the sun. Voyager traveled through this river for decades. Its instruments measured the particles streaming past it. They measured the magnetic field, the sun's own magnetic field, stretched and carried outward by the solar wind, growing weaker with distance but still present, still structured, still recognizably the sun's. A field invisible to every human sense, threading through billions of miles of cold space, still the sun's. And then, at a certain distance, a distance no spacecraft had ever reached before, things began to change. The readings started shifting. The solar wind, still flowing outward, began behaving differently. Voyager's instruments registered something that the models had predicted, and yet which felt, when it arrived in the data, like something genuinely new. But before we reach that boundary, the first true threshold Voyager would cross, we need to understand what the heliosphere's interior is doing, because what it is doing, constantly, silently and visibly, is something that matters to every living thing on this planet. Here is what scientists understood, and what Voyager's measurements confirmed with a precision no previous instrument had achieved. The galaxy is not a peaceful place. Beyond the heliosphere, in the interstellar medium, the space between the stars, there is a constant rain of extraordinarily energetic particles. These are galactic cosmic rays. They are not rays in the sense of light. They are actual particles, protons, atomic nuclei, electrons, accelerated to tremendous energies by violent cosmic events, supernova explosions, the remnants of dying stars, the turbulent magnetic fields around collapsed stellar cores. These particles stream through the galaxy in every direction, constantly, at a significant fraction of the speed of light. And they are genuinely dangerous. Galactic cosmic rays carry enough energy to penetrate solid matter, including living tissue. They damage DNA. They ionize molecules in the cells of living organisms. At the energies and intensities present in the interstellar medium, they represent a radiation environment that would be deeply hostile to complex life as we know it. Now, here is the critical fact that Voyager's measurements helped confirm. Inside the heliosphere, the galactic cosmic ray flux, the number of these particles hitting any given area per second, is dramatically lower than outside it. The solar wind, flowing outward at hundreds of miles per second, creates a kind of pressure that deflects and scatters incoming galactic cosmic rays before they can penetrate deeply into the inner solar system. The heliosphere is not a perfect shield. Some cosmic rays make it through, some reach Earth, and our planet's own magnetic field and atmosphere handle the remainder. But the heliosphere reduces the galactic cosmic ray intensity in the inner solar system by a very significant factor. Voyager confirmed this directly. As Voyager 1 travelled outward and eventually crossed the heliopause, the true outer boundary of the heliosphere, which we will reach in detail shortly, its cosmic ray detector registered an almost immediate dramatic increase in galactic cosmic ray intensity. The moment it crossed outside the heliosphere, the rain of high-energy particles intensified sharply. Inside the heliosphere, shielded. Outside the heliosphere, exposed. The difference was not gradual, it was abrupt. The heliosphere was not merely a theoretical boundary, it was a wall. And on the other side of that wall, the galaxy was far more violent than the space we call home. Imagine you could stand somewhere in the outer heliosphere, perhaps 60 or 70 astronomical units from the Sun, roughly 6 billion miles out. 6 billion miles being 10 times the distance from the Sun to Earth. The Sun behind you would be reduced to a brilliant point of light, far brighter than any star in the sky, but small enough to cover with your thumbnail held at arm's length. In every direction around you, the solar wind would be streaming past, invisible but real, a current of particles you could detect with the right instruments. And if you had a cosmic ray counter in your hand, you would see the numbers stay relatively low, the heliosphere's pressure holding back the galactic particle rain. You're inside the bubble. You are, in the most literal physical sense, inside the sun's protective reach. The warmth you feel from that distant point of light is almost nothing at this distance, but the protection it provides, through that invisible solar wind flowing past you in the dark, is the reason the world you left behind is alive. Every sunrise you have ever seen, every living thing you have ever touched, every generation of life that has existed on this planet, all of it has occurred inside this structure, inside the heliosphere, shielded from the full intensity of the galaxy by the sun's continuous exhalation. You were born inside a bubble. 4.5 billion years in the making, and for your entire life, you have never once felt it, because it has never once failed. Picture the heliosphere as a vast soap bubble floating in the wind. The bubble's skin, thin, shimmering, under constant pressure from outside, is the boundary between the sun's domain and the interstellar medium. Inside the bubble, relatively calm, the solar wind flows, the sun's magnetic field threads through the space, and incoming galactic particles are scattered and deflected before they can reach the center. Now picture a tiny probe, smaller than a family car, crossing the interior of that bubble over decades, measuring the pressure of the wind, the strength of the magnetic field, the count of incoming particles at every point along its path, building a profile of the bubble's interior from the inside out. That was Voyager. That is what its instruments were doing for 30, 40, nearly 50 years of travel, and the profile it built, the data it accumulated across billions of miles, gave scientists their first direct measured understanding of the heliosphere as a real physical structure, not a theoretical prediction. And this is where something genuinely contested enters the picture, a scientific disagreement that has not been resolved, and which Voyager's data has only deepened rather than settled. Scientists have long debated the shape of the heliosphere. The earliest models assumed it would be roughly spherical, a bubble expanding evenly in all directions from the sun. But as the data from Voyager accumulated, and as observations from other instruments, including the Interstellar Boundary Explorer, or IBEX satellite, began mapping the heliosphere from the inside, a more complicated picture emerged. Some scientists now argue that the heliosphere is comet-shaped, compressed on the side facing the direction of the sun's motion through the galaxy, and stretched into a long tail on the trailing side like a bubble pressed against the wind. Others, analysing the same data, argue for a much more symmetrical shape, more like a croissant or a crescent, based on how the solar wind's magnetic field interacts with the interstellar field. Both interpretations are grounded in real data. Both are held by serious scientists using rigorous methods. And as of today, the question of the heliosphere's true shape remains genuinely open. This is not a minor detail. The shape of the heliosphere affects how well it shields the inner solar system from galactic cosmic rays, and therefore, in principle, how hospitable the Earth's radiation environment is to complex life. The answer matters, and we do not yet have it. What Voyager confirmed, beyond the debate about shape, beyond the open questions that remain, is something that no previous instrument had established through direct measurement: that the heliosphere is real, structured, layered, and functioning as a genuine, cosmic shield. The theories from the 1950s and 60s, the calculations built on Eugene Parker's foundational work, were not merely correct in outline. They were describing something that genuinely exists in space and genuinely protects the world we live on. That is not a small thing. For billions of years, this bubble has held. The sun has breathed outward, and the interstellar medium has pressed inward, and the boundary between them has negotiated itself into a shape that keeps the interior, keeps us, in a radiation environment where chemistry can build complexity, where DNA can replicate without constant catastrophic damage, where life, over time, can become what it is. Voyager crossed that entire interior. It measured every layer of it, and then it reached a place where the first great threshold appeared, the first wall within the bubble, and what it measured there was nothing like what scientists had expected to find, because the heliosphere is not simply an open space between the sun and its outer boundary. It has internal structure, and the first layer of that internal structure, the first boundary Voyager crossed on its way outward, is a shock wave, a place where the solar wind, travelling at supersonic speed for billions of miles, suddenly slams into resistance it cannot overpower and does something that no model had fully predicted in the way it actually occurred. Scientists called it the termination shock. They knew it should exist. They thought they knew roughly where to find it. They were wrong about almost everything else. Something was happening to the solar wind. Voyager's instruments were registering it clearly, a change in the readings, a shift in the behavior of the particles streaming past the spacecraft. After nearly 3 decades of travel, after crossing the orbits of every planet in the solar system, after reaching distances no human-made object had ever reached before, Voyager 1 was approaching something. A wall. Not a physical wall, not a surface you could touch or see, but a real boundary, a place in space where the physics of the solar wind changes so abruptly, so dramatically, that the word scientists use for it is a shock. Shocking discovery number 2 is the story of that wall, what it is, how it got there, and why, when Voyager finally crossed it, almost nothing about it was quite what scientists had expected. To understand what the termination shock is, we need to return to the solar wind one more time, because a specific property of it is what creates this boundary in the first place. The solar wind, as it flows outward from the sun, is supersonic. We established that. It moves at hundreds of miles per second, far faster than the speed at which pressure waves can propagate through the plasma. And for billions of miles in every direction, it holds that supersonic speed. It does not slow gradually. It does not ease into the outer solar system at a comfortable pace. It roars outward. But here is the physics that makes the termination shock inevitable. A supersonic flow cannot simply stop being supersonic without consequence. When a supersonic flow, whether it is gas around an aircraft wing or the solar wind in deep space, encounters a region of resistance it cannot simply push through, the physics forces a transition. The flow has to slow down. It has to go from supersonic to subsonic, from moving faster than the local sound speed to moving slower than it. And that transition, in plasma physics as in aeronautics, cannot happen gently. It happens as a shock wave, a sudden, sharp, energetic transition compressed into a relatively thin boundary where the properties of the flow change almost instantly. Picture this. Imagine a fast river striking a shallow section of stream bed. Upstream of that shallow spot, the water flows fast and smooth. At the point where it hits the shallowing bottom, it jumps, suddenly, in a visible turbulent line, and downstream the water moves slower, rougher, more chaotic. That visible jump in the river's surface is called a hydraulic jump. The termination shock is the solar system's equivalent, scaled up by a factor that makes the comparison almost absurd. Instead of a river a few meters wide, we are describing a boundary tens of billions of miles in circumference. Scientists had predicted the termination shock for decades. The theoretical reasoning was solid. If the solar wind flows outward supersonically and encounters the interstellar medium pressing inward, there must be a transition region somewhere out there where the supersonic wind is forced to slow. The physics demanded it. The models described it. There was genuine consensus that the termination shock existed and that any spacecraft traveling far enough outward would cross it. What scientists were not certain about was exactly where it would be. Different models produced different estimates. ranging from roughly 75 to perhaps 100 astronomical units from the Sun. 75 astronomical units is roughly 7 billion miles. That is 7,000 million miles. Approximately 2.5 times the distance from Earth to Neptune, the outermost planet. So the predicted range was vast, but it was a range. Scientists were confident the boundary was real, and roughly confident about where it weighted. They had every reason to believe the story would be clean and confirmatory. Voyager would cross the termination shock. The data would match the models. A major theoretical prediction would be validated, and that was how the story began. In the years before Voyager 1's crossing, scientists began noticing something in the data. The spacecraft's instruments were detecting increases in the intensity of energetic particles, high-speed charge particles that were being accelerated to significant energies somewhere in the outer heliosphere. This was an early sign that Voyager was approaching a region of intense physical activity. The models had predicted that the termination shock would accelerate particles, but the particles Voyager was detecting were arriving in pulses, bursts of intensity that rose and fell as the spacecraft traveled. Scientists realized something important. The termination shock was not stationary. It breathes. The Sun's activity rises and falls in a roughly 11-year cycle, periods of intense solar activity alternating with quieter periods. During more active phases, the solar wind is stronger, and the termination shock is pushed outward by the increased pressure. During quieter phases, it retreats inward. So as Voyager traveled toward it, the shock itself was moving, sometimes toward the spacecraft, sometimes away from it. Voyager was, in a sense, chasing a boundary that refused to hold still, a threshold that shifts like a tide, invisible, vast, and moving. In December of 2004, 27 years after launch, and at a distance of about 94 astronomical units from the Sun, Voyager 1's instruments registered the crossing. 94 astronomical units, that is roughly 8,700,000,000 miles, approximately 8.7 billion miles from the Sun, or 14 billion kilometers. To put that in human terms, the diameter of Neptune's orbit is about 5.5 billion miles. Voyager had traveled more than 1.5 times that orbit's diameter beyond Neptune itself before hitting this first true boundary. The scientists at JPL, who had been watching Voyager's data for years, knew what they were looking for. The solar wind speed should drop suddenly. The magnetic field should pile up, compress, as the slowing wind packed together at the boundary. The energetic particle count should spike, and one by one, reading the telemetry as it arrived, with a signal delay of over 12 hours each way, they watched all of it happen. Edward Stone, Voyager's project scientist since the mission's beginning in 1972, described the moment as one of genuine scientific satisfaction. They had predicted a boundary. They had found it. The theory was confirmed. But the confirmation came with a complication that no one had fully anticipated. Voyager 2 crossed the termination shock in August of 2007, nearly 3 years after Voyager 1. This was expected. Voyager 2 is traveling in a different direction through the solar system. It follows a path angled differently from Voyager 1's, heading toward the southern region of the heliosphere, while Voyager 1 headed toward the north. But here is what was not expected. Voyager 2 crossed the termination shock at roughly 84 astronomical units from the Sun, approximately 7,800,000,000 miles, or about 12.5 billion kilometers, and Voyager 1 had crossed it at 94 astronomical units, about 8.7 billion miles. That is a difference of 10 astronomical units, roughly 930 million miles, nearly a billion miles, between the two crossing distances. Wait, if the heliosphere were symmetrical, if the solar wind pushed outward equally in all directions, both spacecraft should have crossed the termination shock at roughly the same distance from the Sun. The fact that they did not means the heliosphere is not symmetrical. It is compressed on one side and extended on the other, pushed inward by the flow of the interstellar medium against the direction of the Sun's own motion through the galaxy, and stretched outward on the trailing side. The heliosphere was not a sphere. It was being shaped by the galaxy itself, pressed and distorted by the direction and pressure of the interstellar medium flowing around it. Not slightly asymmetrical. Measurably, significantly, structurally asymmetrical. No model of the heliosphere at the time had predicted a difference of that magnitude between the two crossing distances. The models required revision. The picture of the heliosphere as a relatively uniform bubble had to be replaced by something more complex, more dynamic, more responsive to the galaxy's environment than anyone had previously established through direct measurement. The termination shock was not a clean transition. The solar wind on the far side of it was turbulent, chaotic, far more disordered than models had predicted. The magnetic field at the crossing was compressed and tangled, and the energetic particles, the ones being accelerated in the shock region, were more intense than expected and arriving in ways that the standard models struggled to fully explain. The boundary existed. The physics was real, but inside and around the termination shock, the universe was doing something richer, more complicated, and more violent than any model had fully described. You are looking at the first real frontier in the solar system, the first place, traveling outward from the sun, where the universe physically pushes back against our star. Everything inside this boundary belongs, in the deepest physical sense, to the sun. Everything beyond it is in negotiation, a turbulent, churning transition zone where the sun's dominion begins to erode. Voyager crossed that line. It felt the shock, and what it measured there changed the way we understand the boundary of our own solar neighborhood. What Voyager confirmed at the termination shock was a landmark moment in space science. For the first time, a spacecraft had directly sampled the region where the solar wind transitions from supersonic to subsonic flow, and measured the turbulence, the particle acceleration, and the magnetic compression that happened there in real time. The theories were validated in outline. The termination shock was real. The shockwave physics was real. The particle acceleration was real. But the asymmetry, that billion-mile difference between the two crossings, meant that the heliosphere was a more dynamically shaped structure than the models had assumed. And it raised a deeper question immediately. If the termination shock was asymmetrical, what did that mean for everything beyond it? Because beyond the termination shock, the solar wind does not simply reach the outer boundary and stop. There is another region between the shock and the true edge of the solar system, a zone of turbulent, slowed, compressed plasma, a region that scientists had predicted would be relatively straightforward to characterize. They were wrong. What Voyager entered after crossing the termination shock was a region that should, by every model scientists had built, have been a gradual and predictable transition zone. A kind of buffer, slowed solar wind making its way toward the outer boundary, diffusing, calming, preparing to meet the interstellar medium. Instead, it was a storm, chaotic magnetic fields, trapped particles ricocheting through turbulent plasma, a region so energetically active and so structurally disordered that scientists had to create an entirely new framework to describe what was happening inside it. They called it the heliosheath. And what Voyager found there was shocking discovery number 3. After the termination shock, the hard part was supposed to be over. Scientists had spent decades predicting that boundary, calculating where it should be, what it should look like, how the solar wind would behave as it crossed from supersonic to subsonic flow. And when Voyager finally crossed it, when the data confirmed the shock was real and the physics matched the theory in its broad outlines, there was a sense within the scientific community of something like relief. The heliosphere was yielding its secrets. The model was holding. What came next, they reasoned, would be simpler. The region beyond the termination shock, the zone between the shock and the true outer boundary of the heliosphere, was expected to be a gradual, thinning, quieting transition. Slowed solar wind making its predictable way toward the edge. Calm, orderly, describable. Scientists were wrong. Not slightly wrong. Not wrong in one detail or one measurement. Wrong about the fundamental character of the entire region. The region between the termination shock and the outer boundary of the heliosphere has a name. It is called the Helios Heath. The Helios Heath, a word that sounds like what it is, a sheath, an outer layer, a zone that wraps around the inner solar system and separates the sun's domain from the galaxy beyond. It is the buffer zone, the transition space, the last region of the heliosphere before the solar wind gives way entirely to interstellar space. Based on the models scientists had built before Voyager reached it, the Helios sheath was expected to be roughly uniform. Slowed solar wind, subsonic now, after the transition at the termination shock, flowing steadily outward, gradually losing pressure as it approached the outer boundary, becoming thinner and cooler as it went, like the wake behind a moving boat, turbulent close to the hull, but smoothing out as it spreads into the water behind it. Scientists expected the Helios sheath to behave like the far end of that wake, quieter, more settled, easier to characterize. What Voyager found instead is shocking discovery number 3. The Helios sheath is not calm, it is not smooth, it is not a gradual transition, it is a storm zone. As Voyager 1 travelled deeper into the Helios sheath in the years following its 2004 termination shock crossing, its instruments began sending back readings that confused and then genuinely disturbed the scientists analysing them. The magnetic field, which should have been smoothly oriented and steadily declining in strength, was chaotic. It fluctuated, it changed direction, it piled up in ways the models had not predicted, forming compressed regions separated by zones of dramatically different field orientation. Picture this. You are holding a garden hose with the nozzle at full pressure, and you press your thumb over the end to slow the flow. The water that was streaming outward cleanly now has nowhere to go. It swirls, compresses, churns, in the space between your thumb and the nozzle tip. The Helios sheath is something like that space, but instead of a few inches of turbulent water, it spans billions of miles of churning plasma, and instead of a garden hose, the source is a star. The solar wind, which had been flowing outward supersonically for billions of miles, was now slowed, forced to pile up in the Helios sheath because the outer boundary of the heliosphere was pushing back, and rather than thinning smoothly, it was compressing, thickening, becoming denser and more disordered the deeper Voyager travelled into it, like pressure building in a room where all the doors have been locked. There is something worth pausing on here. The scientists reading Voyager's Helios sheath data were not young researchers encountering a fresh problem. Many of them had been working on Voyager for decades. Some had spent their entire professional careers on this mission. Edward Stone, Voyager's project scientist, had held that role since 1972, the year the spacecraft was still being designed. He was in his mid-30s when the mission began. He was in his 70s when Voyager 1 was sending back Helios sheath data that didn't match the models. There is something deeply human in that picture. Decades of careful work, careful prediction, careful expectation, and then the universe hands you a result that says the predictions were not wrong exactly, but incomplete in ways that now need new thinking. Not defeat, something more complicated than defeat. The particular feeling of a scientist confronting reality at the edge of what theory can reach. That is what the Helios sheath data produced. And those scientists kept working. The magnetic field readings were the first and most persistent sign that the Helios sheath was more complex than predicted. In the inner solar system, the sun's magnetic field is carried outward by the solar wind in a well-understood spiral pattern, like the grooves in a vinyl record, curving outward as the sun rotates. This pattern had been measured and confirmed many times. Scientists expected it to persist, modified but recognizable, into the outer heliosphere. But inside the Helios sheath, Voyager's magnetometer, the instrument that measures magnetic field direction and strength, was recording something very different. The field was not following the expected spiral. It was oriented in ways that seemed almost random at times, turning in different directions within relatively short distances, compressing into ridges and thinning into gaps. Scientists found themselves looking at a magnetic field environment that seemed, in some of its features, to be folding back on itself, turning inward toward the sun rather than continuing to stream outward. How do you explain a solar wind magnetic field that turns back toward the sun? The answer, as scientists worked through the data, pointed to the outer boundary. The heliopause, the true outer edge, of the heliosphere was pressing back. The interstellar medium flowing around the heliosphere from outside was creating pressure that the solar wind in the Helios heath had to push against. And in that contest, the magnetic field was being compressed, redirected, and distorted in ways that no model had fully anticipated. Here is where the Helios sheath delivered its most unexpected revelation. Scientists expected the Helios sheath to be a relatively empty transit zone. Slowed solar wind particles making their way from the termination shock to the outer boundary, with galactic cosmic rays from outside beginning to filter in as the heliosphere's pressure weakened. A one-way flow. Particles moving outward from the sun, radiation beginning to filter inward from the galaxy. But the data from Voyager showed something that contradicted this picture directly. Inside the Helios sheath, energetic particles were trapped, not streaming outward, not filtering inward, trapped, bouncing back and forth within the region, accelerated by the chaotic magnetic fields, unable to escape easily in either direction. The Helios sheath was not simply a transit zone, it was a particle trap, a region where the turbulent magnetic environment was capturing energetic particles and holding them, accelerating them to higher and higher energies through repeated interactions with the moving magnetic structures around them. The mechanism is something physicists call Fermi acceleration. Named after Enrico Fermi, the physicist who described it in 1949, Fermi acceleration occurs when charged particles bounce repeatedly between moving magnetic regions, gaining a small amount of energy with each bounce, the way a ball gains energy when bounced between two approaching walls. Over many bounces, the energy accumulated becomes very large, and inside the Helios sheath, the chaotic magnetic environment was providing exactly the conditions for this to happen. The Helios sheath was not a quiet hallway between the termination shock and the outer boundary. It was an accelerator, a natural cosmic particle accelerator, operating over billions of miles, powered by the interaction between the solar wind and the interstellar medium. The magnetic field was chaotic, nothing like the models. Particles were being trapped and accelerated, not predicted. The solar wind was not thinning smoothly, it was compressing and churning. The region was not a gradual transition, it was an active, energetic, structurally complex environment. And then Voyager 2 entered it from a different direction and made the asymmetry undeniable. Voyager 1 travelled through the Helios sheath in a northward direction relative to the plane of the solar system. Voyager 2 travelled through it from a southward angle. They sampled the same region from two different trajectories across a gap of several years, and the data they returned from their respective paths through the Helios sheath was measurably different, not just in detail, but in fundamental character. The magnetic field intensities were different, the particle populations were different. The thickness of the Helios sheath itself, the distance between the termination shock and the outer boundary, appeared different depending on which path the spacecraft travelled. Voyager 2's measurements suggested it was crossing a thinner Helios sheath than Voyager 1 had traversed. This confirmed, with direct physical measurements spanning billions of miles, what the termination shock crossing distances had first suggested. The heliosphere is not symmetrical. The Sun's protective bubble, 4.5 billion years in the making, the structure that shields everything we have ever known, is shaped by forces outside itself, pressed and distorted by the flow of the interstellar medium, compressed on the side facing the Sun's direction of travel through the galaxy, thinner in some directions than others. The heliosphere does not simply contain the solar system, It negotiates its shape with the galaxy, every moment, in every direction at once, and those negotiations are not equal. The galaxy is pushing back. The radiation environment you live in, the background level of cosmic rays reaching Earth's surface, filtered first by the heliosphere, then by Earth's magnetic field, then by the atmosphere, is determined in part by the thickness and character of this region. A thinner heliosheath means less shielding. A more turbulent heliosheath means a different kind of shielding. The storm zone Voyager travelled through is not abstract physics. It is the outer layer of the system that makes Earth's surface livable. Its structure is your structure, in a very real and very physical sense. What Voyager found in the heliosheath was a region that science had predicted in rough outline and misunderstood in almost every important detail. The turbulence was real and unprecedented. The trapped particles were real and unexpected. The asymmetry was real and structurally significant. And the picture that emerged from the data of a heliosheath that is not a quiet buffer zone, but an active, dynamic, magnetically chaotic environment responding to pressures from both inside and outside the heliosphere, permanently changed how scientists think about the structure of our solar system's outer boundary. But the heliosheath was not the last surprise, because as Voyager 1 travelled deeper through this storm zone, measuring, transmitting, slowly approaching the true outer edge, its instruments began registering something new, something the models had not included, a region just inside the heliopause where the behaviour of the solar wind changed again, not at the outer boundary, but before it, a stagnation, a stillness inside the storm, a place where the solar wind slowed, almost stopped and turned back on itself. Scientists did not know what to call it at first. The models had not predicted it. It did not fit neatly into any existing category of heliospheric physics. It appeared in the data as something unprecedented, a region where the rules that governed everything else in the heliosheath seemed, for reasons that were not immediately clear, to break down entirely. They eventually called it the stagnation region, and what it told scientists about the true outer boundary of the solar system, about how close Voyager actually was to crossing out of everything the Sun has ever controlled, was more profound and more unsettling than anyone had prepared for. That is shocking discovery number 4. There is a moment in every long journey when you can feel the destination before you reach it. Not see it, not measure it, feel it, in some shift in the air, some change in the quality of the light, some signal that the terrain has quietly crossed into something new. Travellers know this feeling, sailors know it, the atmosphere thickens, the conditions change. Something ahead is exerting its presence before you have arrived. Voyager 1 felt something like this, not in any human sense. It is a machine, a remarkable one, but a machine. And yet, as it travelled deeper into the heliosheath in the years after 2008, its instruments began registering changes that told scientists, with increasing urgency, that the true outer boundary of the solar system was close. Not just near in the way that everything in the heliosphere is near, relative to the distances of interstellar space, near in a precise, measurable, physically meaningful way, but the way the boundary announced its presence was not what anyone had anticipated, and what Voyager found in that final approach, a zone that no model had ever included, a region that should not have existed, became shocking discovery number 4. To understand what Voyager encountered, we need to understand what scientists were expecting as the spacecraft approached the heliopause. The heliopause, that is the true outer boundary of the heliosphere, the place where the Sun's solar wind finally gives way completely to the interstellar medium, the place where our solar system, in the most physically rigorous sense, ends. Scientists expected that as Voyager approached the heliopause, the heliosheath's turbulence, the chaotic magnetic fields, the trapped particles, the compressed and churning plasma we explored, would gradually give way to a different character. The solar wind would thin, the magnetic field would weaken, and the first signs of interstellar space, galactic cosmic rays filtering in from the other side, interstellar magnetic field influencing the local environment, would steadily increase, building toward the crossing point. A smooth escalation, a graduated transition. The instruments would watch the numbers climb or fall in one steady direction, and at some point the scientist would say, "We are close. Closer. Here." That is not what happened. Between roughly 2010 and 2012, as Voyager 1 travelled through the far outer reaches of the Helios Heath, somewhere between 110 and 120 astronomical units from the Sun, its instruments began returning data that stopped the team cold. 110 astronomical units. That is approximately 10,200,000,000 miles. 10,200,000,000 miles from the Sun. To feel that number, light itself, travelling at 186,000 miles per second, the fastest speed that physics permits, takes more than 15 hours to cross that distance. 15 hours at the speed of light, and Voyager crossed it in 33 years, carried by a nuclear generator, transmitting home on 23 watts of power, less than the bulb above a kitchen sink. At that extraordinary distance, something profoundly unexpected appeared in the data. The solar wind almost stopped, not slowed in the way it had been slowing since the termination shock, not declined in the gradual, predictable way the models described, stopped, or very nearly so. The outward flow of solar particles that had been streaming past Voyager's instruments for over 3 decades essentially ceased. The particles that had been moving, however slowly, in the direction away from the Sun, in the direction Voyager itself was travelling, were no longer moving that way. A river that had flowed for billions of miles suddenly losing its current, without warning, without explanation, and that was only the first part of the anomaly. At the same time the solar wind stalled, Voyager's magnetometer, the instrument measuring the strength and direction of the local magnetic field, registered something equally startling. The magnetic field strength approximately doubled, in a region where the magnetic field had been declining steadily for years, growing weaker with distance as the models predicted. It suddenly surged. The field that the solar wind carries outward from the Sun, the field that had been thinning and weakening across billions of miles of space, compressed sharply and grew nearly twice as intense as it had been just before this region. Picture this. You are pressing a coil of wire tightly in your hands, compressing it into a smaller and smaller volume. As you compress it, the spring's resistance increases and its coils pack together more densely. A magnetic field compressed into a smaller region behaves similarly. Its strength increases as the field lines are forced closer together. What Voyager was measuring was evidence that the magnetic field ahead was being pushed back against itself. Something was stopping it from escaping outward. Something from outside was pressing the field inward, compressing it, concentrating it. The interstellar medium, the boundary, was doing this. The heliopause, the outer wall of the heliosphere, was pressing back against the solar magnetic field, and the field was piling up, doubling in strength, unable to cross to the other side. Voyager was reading the pressure of the boundary before it had even reached it. And then came the third component of the anomaly, and this one genuinely shocked the scientists watching the data arrive. The solar energetic particles, the charged particles produced by the Sun and accelerated through the heliosphere, dropped dramatically. In a region where particle behavior had been turbulent and complex for years, the count of solar particles registered by Voyager's instruments fell sharply, not to zero, but by a very significant factor. Here is why this was so deeply unexpected. Scientists had anticipated that as Voyager approached the heliopause, solar particles would become harder to detect, simply because the spacecraft was getting farther from the Sun, and the particles would be thinning with distance. That part was expected. But the drop that occurred was far too sharp to be explained by distance alone. It was not thinning, it was a collapse, as if the solar particles that had been streaming outward were hitting a wall, and bouncing back, unable to cross into whatever lay beyond. And simultaneously, on the other side of this equation, the galactic cosmic rays, the high-energy particles from deep space that had been increasing as Voyager traveled outward, did not surge through this region the way scientists expected. They held at an elevated but roughly stable level, neither dropping sharply nor surging to the intensities that would indicate open passage. Through the heliopause, solar particles blocked from escaping outward, galactic particles not yet streaming freely inward, magnetic field doubled, solar wind stalled. Scientists were looking at a region that behaved like none of the models had ever described. The solar wind was not flowing outward, the magnetic field had doubled in strength, solar energetic particles had collapsed in count, galactic cosmic rays were elevated but not yet surging freely. Everything was pointing to a single conclusion. This was not the heliopause, but it was something specific, something structured, something real. The scientists at NASA analyzing Voyager 1's data in 2011 and 2012 had a specific problem on their hands, one that was almost philosophical before it was scientific. They were looking at a region of space that had never been predicted, never been modeled, and had no established name or framework to describe it. The data was unambiguous. Something was happening, but what to call it and how to explain it required careful thought. Edward Stone, who had guided the mission through every previous discovery, described the stagnation region data as genuinely puzzling, in a way that the team had not encountered before. The spacecraft was clearly in a transitional state. Something was close, the boundary was near, perhaps a few astronomical units away, perhaps less. But the behavior of the plasma, the particles and the field in this last zone before the edge was structured in a way that demanded its own category. They called it the stagnation region, a name that described exactly what it was, a zone of stillness inside the storm, a place where the outward momentum of the solar wind, which had been travelling in one direction for 4.5 billion years, had essentially spent itself. The wind had come as far as it could. The sun's exhaled breath, which had travelled billions of miles, had reached the last possible distance before it was turned back. And this is the detail that makes the stagnation region truly remarkable, and that reveals more clearly than anything else in the heliosheath how close Voyager was to the true edge. The solar particles that were still detectable in the stagnation region were not merely stalling, they were being redirected. Instead of streaming outward, away from the sun, in the direction Voyager was travelling, they were turning back, inward, toward the sun. The solar wind's outward flow had been sufficiently stopped that the particles it carried were no longer escaping. They were being pushed back by the pressure of the interstellar medium at the heliopause, turned around and returned to the heliosphere. The sun's exhaled particles were being refused exit. There is something quietly profound in this. 4.5 billion years of solar wind, particles that left the sun's outer atmosphere at hundreds of miles per second, that travelled billions of miles outward, that crossed the termination shock and fought through the turbulent heliosheath, arriving at this last region, slowing, stalling, and turning back, denied passage, the galaxy pressing back hard enough to send the sun's own material home. And here is what that means for the world you live on. Everything you know, every person, every city, every landscape, every living thing exists inside a system whose outer boundary is capable of turning back even the sun's own wind. You live inside a structure that the galaxy actively shapes and constrains. The solar system is not simply floating free in interstellar space. It is contained by it, pressed on all sides, negotiating its boundaries moment by moment with forces that dwarf anything in our local neighbourhood. That is the world Voyager was about to leave behind. The stagnation region was not in any model. It was not predicted by any established theory of heliospheric structure. It appeared in Voyager's data as a completely new category of boundary region, specific, measurable, and scientifically rich, and what it told scientists was precisely what its name implies. Voyager 1 had reached the place where the sun's outward momentum had finally, irrevocably, exhausted itself. The edge was close. The true edge, the heliopause, the boundary between the solar system and interstellar space, was somewhere ahead, perhaps just a few billion more miles distant. In the cosmic scale of the journey Voyager had already taken, that was barely a step. And yet, in the nearly half-century of the mission's existence, no instrument, no theory, no model had ever described what would happen in the precise moment of crossing. Because the heliopause is not like the termination shock. It is not a gradual transition into something new. The moment Voyager crossed it, the precise, measurable, documented moment on August 25, 2012, was not a blurring of boundaries or a long, gradual shift. It was a threshold, sharp, clear, a line drawn in space by the physics of two regimes pressing against each other across the full span of the heliosphere. On one side, the sun's domain, 48 years of travel, everything we have ever called home. On the other side, something that no human instrument had ever touched. The fifth discovery is the most profound of all 9, and it happened the moment Voyager crossed that line, and humanity, for the first and only time in all of recorded history, left the solar system. August 25th, 2012. That date will mean nothing to most people who hear it. It was a Saturday. Summer was ending in the Northern Hemisphere. Nothing about that day in the ordinary record of human events marks it as exceptional. But on that day, at a distance of approximately 121 astronomical units from the Sun, approximately 11.2 billion miles, or just over 18 billion kilometers, from the star that created us, a machine the size of a small car crossed a threshold that no object made by human hands had ever crossed before. It left the solar system. Shocking discovery number 5 is not a measurement anomaly. It is not a data point that required years of interpretation. It is not a phenomenon that scientists argued about and eventually categorized. It is a crossing, a moment, the most extraordinary moment in the history of space exploration, and, in a very real sense, in the history of our species. To understand what it means, we need to be precise about what the heliopause actually is. The heliopause, the true outer boundary of the heliosphere, is the place where the solar wind ends, not slows, not thins, ends. It is the boundary where the particles exhaled by the sun over billions of years, the same solar wind that creates the termination shock, that fills the heliosheath, that turns back in the stagnation region, finally run out of outward momentum and yield completely to the interstellar medium flowing in from the galaxy. On one side of the heliopause, the sun's domain, solar particles, solar magnetic field, the physics of a system governed by our star. On the other side, the local interstellar medium, the space between the stars, the galaxy's own particles, its own magnetic field, its own ancient and unbroken silence, a silence that has existed since long before the sun formed, before the earth formed, before any of the atoms in your body were assembled into anything capable of caring about silence. The heliopause is not a wall you can see or touch, but it is as real as any physical boundary in nature, and crossing it means something that no previous human achievement had ever accomplished. It means leaving home. The confirmation of Voyager 1's heliopause crossing did not come from a single instrument or a single moment. It came from multiple independent measurements converging on the same conclusion simultaneously, and the convergence was sharp enough that there was ultimately no reasonable alternative interpretation. First, the solar energetic particles. In the stagnation region, they had already dropped dramatically, but as Voyager 1 crossed the heliopause, they did not merely drop further, they essentially vanished. The particles produced by our sun, The particles that had been Voyager's constant companions for 35 years of travel were gone, reduced to near zero. The solar wind in every measurable form had stopped. There was nothing coming from the sun. Voyager was beyond its reach, the quiet that arrives when every familiar sound has simply ceased. Second, the galactic cosmic rays. On the other side of the equation, the high-energy particles streaming in from the galaxy, the ones the heliosphere had been partially deflecting throughout the spacecraft's journey, surged, not gradually, sharply. In the immediate aftermath of the heliopause crossing, Voyager 1's cosmic ray detector registered an abrupt, sustained increase in galactic cosmic ray intensity. The shield was gone. The galaxy's radiation, previously moderated by the heliosphere, was now arriving at full, unfiltered intensity. Third, and this is the measurement that settled the debate, the magnetic field. Here is where the science becomes genuinely elegant, and where a debate that ran for over a year was finally resolved. When Voyager 1's data from mid-2012 first arrived at JPL and scientists began analysing it, there was immediate recognition that something extraordinary had happened. The solar particle counts had collapsed. The galactic cosmic rays had surged. These measurements strongly suggested a heliopause crossing, but there was one piece of evidence that some scientists felt was still ambiguous. The magnetic field. Here is the subtlety. At the heliopause, scientists expected not just a change in particle populations, they expected the magnetic field itself to change direction. The solar magnetic field, carried outward by the solar wind for billions of miles, has a specific orientation dictated by the sun's rotation and the direction of the solar wind's flow. The interstellar magnetic field has a different orientation, set by the galaxy's own large-scale magnetic structure. At the heliopause, the field should rotate, shift direction, marking the transition from one magnetic environment to the other. The initial data showed the field strength changing, but the direction of rotation was not what some models had predicted. A debate opened in the scientific community. Had Voyager truly crossed the heliopause, or was it passing through some previously uncharacterized internal region of the heliosphere? This is a real, documented scientific disagreement, and it was not trivial. Serious scientists on both sides presented rigorous arguments from the same data. The resolution came through Voyager 1's plasma wave instrument, an instrument that detects oscillations in the plasma, the electrically charged gas, around the spacecraft. In 2013, scientists analyzed plasma wave data from late 2012 and early 2013 and found that the density of the plasma around Voyager 1 had increased dramatically, to levels consistent with the interstellar medium, not the heliosheath. The plasma outside the heliopause is denser than the plasma inside it because the interstellar medium is a different physical environment. Voyager was measuring that denser plasma. It was outside. The crossing was confirmed. August 25, 2012. The formal scientific announcement of Voyager 1's interstellar crossing came in September of 2013, just over a year after the crossing itself occurred, because that is how careful science works. Edward Stone, who had guided the mission for more than 40 years, stood before journalists and colleagues and described what the data showed. He had spent the previous months working through competing interpretations, examining the plasma wave evidence, consulting with colleagues around the world. When the announcement came, it was not made with fanfare or ceremony beyond what the facts warranted. It was stated clearly, supported by data, and allowed to carry its own weight. Stone noted that Voyager had entered a new region of space, one that no model had fully prepared them for in its specific details, even as the broad prediction of the heliopause had been correct. A 40-year journey guided by a team that had aged alongside the spacecraft had produced humanity's first direct measurement of interstellar space. 121 astronomical units, 11.2 billion miles, approximately 18 billion kilometers. That is the distance at which Voyager 1 crossed the heliopause. To feel that number fully, the sun's light takes 8 minutes and 20 seconds to reach Earth. It takes that same light nearly 17 hours, not minutes, hours, to reach Voyager 1 at the heliopause distance. So when mission controllers at JPL sent a signal to Voyager 1 on the day of the crossing, the signal took approximately 17 hours to arrive at the spacecraft. And they had to wait another 17 hours, just over 34 hours total, to receive any response. That's nearly a day and a half of waiting, just to confirm that their command had been received. A machine 11 billion miles away, still listening, still responding, still transmitting. If you could be at Voyager 1's position at the moment of crossing, standing somehow at the heliopause, here is what the instruments would tell you, translated into sensation. Behind you, in the direction of the sun, the faintest trace of solar particles would be thinning to nothing. Ahead of you, the galactic cosmic rays would be arriving with a new and unmistakable intensity, not dangerous to feel, but measurable, present, ancient. The magnetic field threading through the space around you would be subtly different in its orientation from the field you had traveled through for billions of miles. And the plasma, the thin, ionized gas surrounding you, would be denser than anything in the heliosphere, thicker and quieter in its own way. You would not see a line, you would not feel a wall, but every instrument in your hands would be telling you the same thing. The sun is no longer the authority here. You have crossed into a space that belongs to no star. Solar particles, gone. Galactic cosmic rays, surging. Plasma density, interstellar. Magnetic field, confirmed rotated. 35 years of travel. Humanity had left the solar system. There is something worth sitting with here. The solar wind, whose existence Eugene Parker predicted in 1958, whose reality was doubted and dismissed before it was confirmed, whose long journey outward from the sun created the very heliosphere that Voyager spent decades crossing. That wind had carried Voyager's magnetic measurements all the way to the edge of the sun's domain. The particles Parker described had traveled with Voyager for 11.2 billion miles. And then, at the heliopause, they stopped. They could not cross. But the knowledge they had given us could. The understanding Parker built, the instrument teams flew, the data analysts interpreted, that crossed with Voyager into interstellar space, even as the solar wind itself turned back. And here is the weight of it, placed where it belongs, on you tonight, watching this. Every civilization that has ever existed on this planet, every city, every language, every scientific tradition, every human being who ever looked up at the night sky and wondered what lay beyond, all of it occurred inside the solar system, inside the heliosphere, under the sun's protection. Every human life ever lived has been lived inside the boundary. Voyager crossed on August 25th, 2012. And on that day, for the first and only time in the 4.5 billion year history of the solar system, something made by human hands passed through that boundary and continued outward, into the galaxy, on behalf of all of us who remained behind. 6 years, 2 months, and 9 days after Voyager 1's crossing, Voyager 2, travelling in a different direction through the heliosphere, through a southern trajectory that had already shown the asymmetry of the termination shock and heliosheath, crossed its own heliopause. The date was November 5th, 2018, 41 years, 2 months, and 1 day after launch. Voyager 2's crossing came at approximately 119 astronomical units from the Sun, roughly 11 billion miles, or 17.8 billion kilometers. Slightly closer to the Sun than Voyager 1's crossing distance of 121 astronomical units, which was consistent with the asymmetry the mission had been documenting since the termination shock findings in 2004 and 2007. And Voyager 2's crossing provided something Voyager 1 could not by itself deliver: confirmation that the heliopause is a real, coherent, physically consistent boundary, not an artifact of one spacecraft path or one instrument set's readings. 2 spacecraft, 2 different directions, 2 different crossing distances, separated by nearly 2 billion miles of space and 6 years of time, both confirming the same physics, both measuring the same dramatic transition from solar environment to interstellar environment. The boundary was real. The solar system's edge had been crossed twice, and humanity, in its first small, extraordinary, unprecedented step, had twice sent something beyond it. What Voyager's heliopause crossings established, confirmed, measured, documented, is the most fundamental boundary in our local cosmic geography. The heliosphere is real. The interstellar medium is real. The transition between them is sharp, structured, and physically precise. The models that predicted the heliopause's existence were correct in outline. The details, the stagnation region, the asymmetry, the exact location of the crossing, required revision and expansion. But the boundary itself existed exactly where the physics demanded it should. And the fact that we knew to look for it, that Eugene Parker's theoretical work from the 1950s, refined by generations of scientists across 60 years, led to a mission that crossed the boundary and confirmed its existence, is one of the most complete arcs in the history of science. A prediction, a mission, a crossing, a confirmation, all of it connected, all of it real. But the crossing did not end the discoveries, because beyond the heliopause, Voyager's instruments continued operating, and what they found in the space beyond, in the local interstellar medium that no instrument had ever directly sampled, was not the featureless void that most people imagine when they think of the space between the stars. It was active, it was structured, and the first thing Voyager measured in that new environment, the thing that floods in the moment the heliosphere's protection ends, revealed something about the galaxy's radiation environment that every future mission beyond our solar system will have to contend with directly. Galactic cosmic rays, flooding in from every direction, ancient, energetic, relentless. The same particles that the heliosphere had been partially deflecting for the entire history of life on Earth were now surrounding Voyager at their full, unfiltered intensity. And what that means for the future of deep space travel, for the future of any human presence beyond the solar system, is something we have only just begun to understand. That is shocking discovery number 6. Most people, when they imagine the space between the stars, imagine peace, and it is an understandable picture. Vast emptiness, dark silence, nothing moving, nothing colliding, nothing disturbing the perfect stillness of the interstellar void. The universe as a kind of deep, cold calm, hostile to life in its temperatures and pressures, but otherwise quiet, passive, still. That picture is wrong in ways that matter enormously. The space Voyager entered on August 25, 2012, the local interstellar medium, the region between the stars, is not peaceful. It is saturated, flooded, continuously, relentlessly penetrated by some of the most energetic particles in the known universe, arriving from every direction at once, passing through solid matter as though it barely exists, carrying energies that no particle accelerator built by human hands has ever matched. And the moment Voyager crossed the heliopause and its cosmic ray detector registered what was on, the other side, the reading told a story that every future human mission beyond the solar system will have to reckon with. This is shocking discovery number 6. To understand what Voyager measured beyond the heliopause, we need to understand what galactic cosmic rays actually are, because the name, while evocative, does not quite prepare you for the reality. Galactic cosmic rays are not rays in the sense of light or radio waves. They are particles. Real, physical particles, mostly protons, which are the positively charged cores of hydrogen atoms, along with heavier atomic nuclei and some electrons, moving through the galaxy at extraordinary speed. Not the speed of the solar wind, which is hundreds of miles per second, not even the speed of a fast particle accelerator beam. Cosmic rays travel at a significant fraction of the speed of light, Some of the most energetic ones, the highest energy cosmic rays ever detected, travel at speeds so close to the speed of light that the difference is essentially immeasurable with current instruments. Where do they come from? From violence, from the most energetic events in the galaxy, supernova explosions, the catastrophic deaths of massive stars that release more energy in seconds than our sun will release in its entire 10 billion year lifetime. From the turbulent regions around pulsars, the dense, rapidly spinning remnants of collapsed stars, where magnetic fields of extraordinary strength accelerate particles to extraordinary velocities, from distant active galactic nuclei, the violently energetic cores of galaxies powered by supermassive black holes, hurling particles outward across millions of light years. These particles have been traveling through the galaxy, in some cases, for millions of years. They stream through the Milky Way in every direction simultaneously, a continuous, ancient, never-ending rain of particle radiation, a rain that has been falling since before the Earth existed and will continue long after it is gone. Scientists had understood for decades that the heliosphere provides some degree of shielding against galactic cosmic rays. This was not a theoretical abstraction. It was observable directly from Earth. Here is the evidence. The intensity of galactic cosmic rays measured at Earth varies in a clear, predictable pattern that tracks the Sun's activity cycle. During periods of high solar activity, when the solar wind is stronger and the heliosphere is pushing outward with greater pressure, the galactic cosmic ray count at Earth goes down. During periods of low solar activity, when the solar wind weakens and the heliosphere relaxes inward, the count goes up. This inverse relationship, called the Forbush modulation, named after the physicist Scott Forbush, who documented it in the 1930s and 40s, is direct physical evidence that the heliosphere is actively deflecting and scattering incoming galactic cosmic rays before they reach the inner solar system. The stronger the heliosphere, the more it deflects. The weaker it becomes, the more radiation gets through. Scientists knew this. The shielding effect was established physics. What no instrument had ever directly measured until Voyager was the intensity of galactic cosmic rays on the far side of the heliopause, outside the shield entirely, in the raw, unmoderated interstellar environment. How much worse was it out there? The answer, when Voyager 1's cosmic ray detector registered it in real time during the heliopause crossing, was striking. The moment Voyager 1 crossed the heliopause, the cosmic ray count did not gradually increase. It jumped. Sharply, abruptly. In a matter of days, a span of time so short relative to the decades of travel that preceded it, the particle count registered by Voyager's cosmic ray detector surged by approximately double the level it had been measuring in the inner heliosheath. Double, in days. Think about what that means physically. On one side of a boundary spanning billions of miles in circumference, inside the heliosphere, the galactic cosmic ray intensity is at a certain level. On the other side, outside the heliopause, in the local interstellar medium, it is roughly twice as high. The heliosphere is not a perfect shield. It does not block all incoming cosmic rays, but it reduces the bombardment significantly, and that reduction, accumulated over the 4.5 billion years since the heliosphere formed, has been one of the quiet conditions that made Earth's radiation environment hospitable enough for life to develop complex biology. Picture this. You have been standing in a room all your life, and the walls are slightly tinted, not opaque. Light still comes through, but some of it is filtered. You have never noticed the filtering because you have never stood outside the room, and then one day you step outside. The light is the same color. The warmth is the same warmth, but the intensity is different in a way that is immediately measurable, and you realize standing there that the room has been protecting you in a way you never had reason to notice before. That is what Voyager 1 measured at the heliopause, the difference between inside the room and outside it. Here is where the discovery becomes directly relevant to the future of human exploration, and where the numbers deserve to be felt clearly. Galactic cosmic rays carry extraordinarily high energies. Energy in particle physics is measured in units called electron volts, a unit so small that a single photon of visible light carries only a couple of electron volts. A galactic cosmic ray proton typically carries energies in the range of billions to trillions of electron volts, energies so far beyond anything in the solar wind that comparing the two is like comparing a gentle summer breeze to a hurricane wind strong enough to strip bark from trees. At these energies, cosmic ray particles do not simply bounce off matter. They penetrate, they pass through metal shielding, they pass through the walls of spacecraft, they pass through human tissue, and as they do, they ionize molecules along their path. They knock electrons free from atoms, disrupting chemical bonds, breaking DNA strands, damaging the cellular machinery of biology in ways that accumulate with continued exposure. On Earth, we are protected by 3 layers of shielding simultaneously. The heliosphere reduces the incoming cosmic ray flux from outside. Earth's own magnetic field deflects a further portion of those that make it through the heliosphere. And the atmosphere, 100 kilometers, about 62 miles, of air above your head, equivalent to roughly 10 meters of solid water in terms of radiation shielding, absorbs much of what remains. 3 nested layers of protection, all working simultaneously all the time. Remove those layers and step outside them, heliosphere, as Voyager has done. And the raw, cosmic ray environment is what Voyager's instruments have been measuring since 2012. Not theorized, not estimated. Directly measured, in real time, by a spacecraft that is living in it. This is the discovery that transforms the Voyager mission from a historical achievement into a practical imperative for the future. Because if humanity ever seriously intends to send people beyond the solar system, or even to destinations far into the outer solar system, where the heliosphere's shielding begins to thin, the radiation environment Voyager measured is the environment those people will inhabit. Cosmic rays do not care about the ambitions of civilizations. They have been crossing the galaxy at nearly the speed of light for millions of years, and they will continue doing so long after every spacecraft we have ever built has gone silent. Understanding their intensity, their energy distribution, their behavior in the local interstellar medium is not optional for the future of human space exploration. It is foundational. Voyager's cosmic ray detectors captured the first direct measurements of galactic cosmic ray intensity in interstellar space. The intensity was roughly double what it had been just inside the heliopause. The energy spectrum of the particles matched theoretical predictions for interstellar cosmic rays, but the specific details of the spectrum provided new data that models had not fully anticipated. Every reading Voyager sends back is still the only direct measurement of this environment that humanity possesses. No other instrument is out there. No other data exists. And here is where the science opens into a genuinely unresolved question. One that matters not just for future human missions, but for understanding the deep history of life on Earth. The heliosphere's shielding is real. Voyager confirmed that directly. But how much does it actually matter for life? How significant is the difference between the cosmic ray environment inside the heliosphere and outside it in terms of biological impact over geological time? There is an ongoing scientific debate about this question, and it has not been resolved. One position, held by a number of researchers, argues that the heliosphere's shielding, while real and measurable, is not the primary factor protecting life on Earth. Earth's magnetic field and atmosphere do the heavy lifting, in this view, and the heliosphere's contribution, while meaningful, is secondary. Life on Earth has survived periods in the past when the heliosphere was likely weaker, during times of reduced solar activity across extended cycles, and has not been catastrophically disrupted. The other position argues that across very long timescales, hundreds of millions of years, the heliosphere's shielding history may have mattered more than the short-term perspective suggests. Some researchers have proposed that as the Sun moves through different regions of the galaxy during its 230 million-year orbit of the Milky Way. It passes through denser regions of interstellar material, which may compress the heliosphere and reduce its shielding. And some studies have suggested that periods of increased cosmic ray exposure at Earth may correlate, imperfectly, but meaningfully, with periods of elevated mutation rates or climatic instability in the geological record. Neither side has definitively won this argument. The data is incomplete, the correlations are contested, and Voyager's direct measurements of the interstellar cosmic ray environment are one of the key inputs that future models will use to refine these calculations. The heliosphere may be more important to the history of life on Earth than we currently know, or it may be less. The honest answer, right now, is that we are still learning to ask the question properly. There is something worth pausing on here, something that sits outside the data, outside the models, outside the energetics of particle physics. Voyager 1 is currently more than 15 billion miles from Earth, roughly 24 billion kilometers, traveling outward at about 38,000 miles per hour, about 61,000 kilometers per hour, and its cosmic ray detector is still working, still counting particles, still sending home measurements from a radiation environment that no human will visit for generations, if ever. A machine built in the 1970s with less computing power than a pocket calculator is, right now, doing science in interstellar space, quietly, persistently, without anyone aboard to notice whether the instruments are functioning or the data is coming through. It simply keeps going and keeps transmitting. What Voyager's cosmic ray measurements established is a new baseline for our understanding of the local interstellar environment. The heliosphere shields us, meaningfully, measurably, from a radiation environment that is significantly more intense than what we experience on Earth or in the inner solar system. The shield is not perfect. Cosmic rays still reach us. But the difference between inside and outside the heliopause is a real, quantified, scientifically documented difference. Not an assumption or a theoretical projection, but a measured fact. And that fact comes with a weight that compounds as we think about the future. Any mission that carries human beings into the deep outer solar system, let alone beyond the heliosphere, will be carrying those people into the radiation environment Voyager has been measuring since 2012. The cosmic ray shielding problem for human deep space travel is not an engineering detail to be solved later. It is one of the fundamental physical challenges of the endeavor. Voyager identified it. Precisely. With data. The discovery does not close a chapter in space exploration. It opens one, and the opening is vast. But the cosmic ray surge was not the only thing Voyager's instruments detected in the interstellar medium, because as the spacecraft settled into its new environment, beyond the heliopause, surrounded by the thin plasma of the local interstellar medium, one of its instruments began detecting something that no scientist had specifically predicted in the way it appeared. A vibration, a faint, persistent oscillation in the plasma around the spacecraft. Not a burst, not a transient event, not a spike and a return to quiet. A continuous low-level hum, running through the interstellar medium as far as the instrument could detect in both directions along Voyager's path. Scientists, when they converted those plasma oscillations into the closest human perceivable equivalent, called it the cosmic hum. And what it revealed about the character of the space between the stars was more surprising than almost anyone had expected. That is shocking discovery number 7. There is a sound coming from the space between the stars, not a metaphor, not a poetic approximation, a real, measurable physical vibration running through the thin plasma of the local interstellar medium, continuous and persistent, carrying information about the character of the galaxy's own quiet interior. Voyager 1 is hearing it right now. Not with ears, it has none, but with an instrument called a plasma wave detector, which measures the oscillations of electrically charged particles in the space around the spacecraft, the way a microphone measures the compression and rarefaction of air molecules near a sound source. And when scientists at the University of Iowa, analyzing data from that instrument in a study published in 2021, converted those plasma oscillations into sound waves that a human ear could hear, what they produced was extraordinary in its simplicity: a hum, faint, steady, continuous, the voice of the interstellar medium itself. This is shocking discovery number 7. The plasma wave instrument on Voyager 1 was not built to listen to the interstellar medium. It was built to study plasma waves in the planetary magnetospheres, the invisible magnetic environments around Jupiter and Saturn, during the mission's original planetary tour in the late 1970s and early 1980s. It recorded the eerie, whistling electromagnetic signatures of Jupiter's radiation belts, the complex plasma interactions around Saturn's rings, phenomena that scientists had never measured directly before. But the instrument kept working, long after the planets were behind it, long after the planetary mission ended and the interstellar mission began. And as Voyager 1 travelled deeper into the heliosheath and eventually crossed the heliopause, that instrument continued sampling the plasma environment around the spacecraft, recording oscillations in the charged gas, measuring how that gas responds to disturbances, transmitting the data home across a signal delay of more than 23 hours each way. Plasma waves, let us be precise about what they are. In an electrically charged gas, plasma, disturbances propagate as waves, the way ripples propagate across the surface of water. When a solar flare or a coronal mass ejection, a large eruption from the sun's surface, sends a disturbance outward through space, that disturbance can trigger oscillations in the plasma it encounters. The frequency of those oscillations, how quickly the plasma vibrates back and forth, is directly related to the density of the plasma. Dense plasma oscillates at higher frequencies. Thin plasma oscillates at lower frequencies. By measuring the frequency of the oscillations, scientists can calculate the density of the medium they are occurring in. That is the physics, and it is elegant. One measurement, frequency, gives you one fact, density, clean, precise, and in the case of the interstellar medium, extraordinary in what it reveals. Here is what scientists expected to find in the interstellar plasma beyond the heliopause. The interstellar medium was thought to be extraordinarily thin, and it is. The density of the gas between the stars in our region of the galaxy is roughly 1/10 of a hydrogen atom per cubic centimetre, 1/10 of a single atomic nucleus per cubic centimetre, a volume about the size of a sugar cube. To feel that number, the air you are breathing right now contains approximately 27 million trillion, 27 followed by 18 zeros, molecules per cubic centimetre. The interstellar medium contains roughly 1/10 of a single atom per cubic centimetre. It is not merely thin, it is the closest thing to nothing that exists in nature. Because the interstellar medium is so thin, scientists expected its behaviour to be similarly minimal. Not completely passive, the physics of plasma does not permit true silence, but close to it, quiet, still. A medium so sparse that disturbances passing through it would be faint and quickly damped, like a drum struck with a feather in an empty cathedral. What the plasma wave instrument actually detected as Voyager 1 settled into the interstellar medium after the heliopause crossing was something quite different. Activity. Persistent, ongoing, measurable plasma wave activity, not triggered by a specific solar event, not associated with a passing disturbance, but present continuously, running through the interstellar gas as a steady background condition. Stella Koch-Ocker and her colleagues at Cornell University and the University of Iowa, analyzing the Voyager 1 plasma wave data in a study published in the journal Nature Astronomy in May of 2021, found that the plasma emission was consistent across large stretches of interstellar space, detectable over distances of many hundreds of millions of miles, present in Every interval of data they examined, the interstellar medium was not quiet. It was humming, a sound so old and so vast that no instrument in human history had ever been positioned to hear it before. Let us be precise about what the cosmic hum is, because precision here deepens rather than diminishes the wonder of it. The plasma wave instrument on Voyager 1 measures electrical oscillations, fluctuations in the electric field surrounding the spacecraft, generated by the motion of charged particles in the plasma. These oscillations occur at specific frequencies that are far too high for human ears to hear directly. The frequencies Voyager measures in the interstellar medium are in the range of roughly 2 to 3 kHz, 2,000 to 3,000 oscillations per second, which is actually within the range of human hearing, unlike many space plasma frequencies that require mathematical shifting to bring into audible range. 2 to 3 kHz, that is roughly the frequency range of a human voice in normal conversation, a middle frequency, not a deep bass rumble, not a high-pitched whine, a quiet mid-range tone. When scientists at the University of Iowa converted Voyager's plasma wave data directly into sound, simply mapping the measured electrical oscillations into audio output at their natural frequencies, what emerged was a low, steady, narrow-band tone. Narrow-band means it occupies a specific, consistent frequency rather than spreading across a broad range of pitches. It is not a roar or a rush or a complex mixture of sounds. It is a single, persistent note, quiet, clear, and continuous. The cosmic hum, the sound of the local interstellar medium vibrating around a spacecraft, traveling through it at 38,000 miles, 61,000 kilometers per hour, more than 15 billion miles from the world that built it. Picture this. You are holding a wine glass by the stem. You wet your finger and run it. Along the rim, the glass begins to sing, a clear, sustained tone. Now, picture a thinner glass. The tone is higher, a thicker one, lower. The frequency of the singing tells you something real and physical about the glass, its dimensions, its composition, the properties of the material vibrating. The sound is information. That is what the cosmic hum is for the interstellar medium. The frequency of the plasma oscillations Voyager is measuring is information, direct, physical data about the density of the gas surrounding the spacecraft, and the density value that emerges from those measurements, roughly 1/10 of an electron per cubic centimeter, consistent with theoretical predictions for the local interstellar medium, is the first direct in situ measurement of the interstellar plasma density that science has ever obtained. Not inferred from observations of distant gas clouds, not estimated from models of the interstellar medium's large-scale structure, directly measured by a spacecraft sitting inside it, listening. That is a remarkable thing. But what made the 2021 study particularly significant was not just the detection of the hum itself, it was the evidence that the hum is persistent, continuous, present across every interval of data the team analysed, even between the solar events that had previously been the trigger for detectable plasma oscillations in Voyager's interstellar data. Here is the distinction. Before this study, plasma wave detections from Voyager 1 in the interstellar medium had been associated with specific events, moments when a large solar eruption from the Sun sent a disturbance outward through the heliosphere, across the heliopause, and into the interstellar medium, triggering a measurable plasma oscillation that Voyager's instrument captured as it passed. Those event-triggered detections were dramatic and scientifically valuable, but they were episodic, tied to the Sun's activity, not to the interstellar medium's own ambient state. What Koch-Ocker and her colleagues found was something different. Between those event-triggered spikes when the Sun was quiet and no obvious disturbance was propagating through the medium, the plasma wave instrument was still detecting a signal, a weaker signal than the event-triggered peaks, but consistent and persistent. The interstellar medium itself, without any external trigger, was oscillating, This means the interstellar medium has its own internal activity, its own baseline dynamics that are independent of what the Sun is doing. The space between the stars is not a passive medium waiting for disturbances to pass through it. It has ongoing behavior. It hums to itself in the dark between the stars, for reasons that scientists are still working to fully understand. The interstellar medium is alive in a way the models had not fully captured. The light from the nearest star beyond our Sun, Proxima Centauri, takes 4.2 years to reach Earth. 4.2 years, travelling at 186,000 miles per second. The entire volume of space between here and there, an unimaginable ocean of distance, is filled with this thin, humming plasma. The same medium Voyager is travelling through right now, the same oscillations its instrument is measuring, and when in some future era that none of us will live to see, a spacecraft or a signal travels from here to there, it will travel through this hum, through this thin, active, never-silent medium, through an ocean that Voyager has shown us for the first time is not empty, but listening, vibrating with its own ancient, quiet voice. The plasma wave instrument built for planetary work in the 1970s, still functioning in interstellar space nearly half a century after launch, measuring oscillations in gas so thin it barely qualifies as matter, detecting a persistent hum that no model had specifically predicted, proving that the interstellar medium is more dynamic than science had assumed. A 5-year mission, still listening, still discovering. What the cosmic hum represents beyond its immediate scientific content is something that is genuinely moving when you sit with it. Voyager 1 was sent to photograph planets. It was expected to go quiet after 5 years. Instead, nearly 5 decades later, it is floating in the space between the stars, listening to the universe hum to itself, and sending those measurements home, one photon at a time, across a distance that light takes more than 23 hours to cross. The hum is real. The measurement is direct. The density of the local interstellar medium, a number that theorists had estimated for decades from indirect evidence, is now a measured, confirmed value, obtained by the only instrument that has ever been inside the interstellar medium to measure it. And the activity of that medium, its ongoing, self-sustaining plasma, oscillations, independent of external triggers, tells us that the space between the stars is not the featureless void that the phrase empty space implies. It is a physical medium with its own properties, its own dynamics, its own quiet but persistent behavior. The universe, it turns out, does not go silent just because we are not listening. But the cosmic hum was not the only structural revelation that Voyager's time in the interstellar medium produced. Because even as scientists were interpreting the plasma wave data, other measurements, taken by Voyager itself and cross-referenced with observations from Earth-based instruments and the Interstellar Boundary Explorer satellite, were building toward a discovery about the heliosphere's overall shape that challenged one of the most basic assumptions in the field. The heliosphere, the protective bubble we have been traveling through for this entire story, does not look the way scientists drew it on paper for decades. Its shape, its proportions, the way it interacts with the interstellar medium flowing around it, all of it is stranger, more complex, and more consequential than any model predicted. That is shocking discovery number 8. For as long as scientists had been drawing the heliosphere on paper, which is to say, for as long as the heliosphere had been a concept worth drawing, they drew it the same way. A sphere, the sun in the center, radiating its wind outward in every direction equally, creating a bubble of equal dimensions on all sides, symmetrical, balanced, clean, the kind of shape that mathematical elegance suggests when a single source pushes outward against a uniform resistance. It was a beautiful picture, simple, logical, and for decades, no data existed to contradict it directly. But Voyager, first through the termination shock asymmetry in 2004 and 2007, then through the helios sheath measurements across different trajectories, and finally confirmed by cross-referencing its data with observations from other missions, was slowly and irrevocably dismantling it. The heliosphere is not a sphere, and what it actually looks like and why is a discovery that changes how we understand our solar system's relationship with the rest of the galaxy. This is shocking discovery number 8. To appreciate why the shape of the heliosphere matters, we need to hold in mind what the heliosphere actually is, not merely as an abstract boundary, but as a physical structure moving through a physical environment. The Sun is not stationary in the galaxy. It orbits the center of the Milky Way, completing one full circuit approximately every 225 to 250 million years, a journey so vast that in the entire history of complex animal life on Earth, the Sun has not completed even a single full orbit. It has travelled perhaps 40% of one circuit since the first fish appeared in the oceans. As the Sun moves, it moves through the interstellar medium, that thin plasma of gas and magnetic field that fills the space between the stars. And the interstellar medium is not perfectly uniform. It has its own flow, its own structure, its own magnetic field orientation, its own pressure. And the direction of that flow relative to the Sun's motion through the galaxy creates a specific, predictable effect on the heliosphere's shape. The interstellar medium is flowing against one face of the heliosphere, the face pointing in the direction the Sun is travelling. That upstream face is compressed. The other side, the downstream face pointing away from the direction of travel, is stretched outward by the solar wind, which has less resistance to push against there. This much in broad outline was always expected. The models included it. The heliosphere was always going to be somewhat elongated, like a raindrop or a comet, compressed at the front and extended at the back. The question was, by how much? In what direction? And how complex were the distortions beyond this basic elongation? The answers turned out to be far more complicated than anyone had anticipated. The evidence that the heliosphere's shape departs significantly from a simple sphere came from multiple independent directions simultaneously, which is exactly the kind of convergence that scientists trust most, because it rules out instrument error and observer bias in a way that a single measurement never can. The first line of evidence, the one we have been building towards since Chapter 4, was the termination shock-crossing asymmetry. Voyager 1 crossed at approximately 94 astronomical units, roughly 8.7 billion miles, from the Sun. Voyager 2 crossed at approximately 84 astronomical units, about 7.8 billion miles, a difference of nearly a billion miles between two spacecraft travelling in different directions. That 10 astronomical unit discrepancy was not a measurement error, it was a shape. The termination shock is not a sphere, it is closer to an oval, compressed on one side and extended on the other. The Helios heath, the region between the termination shock and the heliopause, showed corresponding asymmetries in its thickness. Voyager 2's measurements suggested a thinner heliosheath in the southern direction it was travelling. Voyager 1's measurements showed a thicker heliosheath in the northern direction. The bubble is not evenly padded. Space shaped by forces so large they bend a structure billions of miles across as easily as wind bends a candle flame. But the deepest challenge to the spherical model came from an entirely different instrument, observing from an entirely different vantage point. In 2008, the same year Voyager 1 was deep in the Helios sheath, measuring its turbulence and chaos, NASA launched a small satellite called the Interstellar Boundary Explorer, or IBEX. The mission was straightforward in concept and extraordinary in ambition: map the heliosphere from the inside out. Not with a spacecraft travelling through it, but by detecting a special class of particles called energetic neutral atoms, particles that form at the heliosphere's boundaries and travel inward toward Earth in straight lines, carrying information about the conditions at the edges of the heliosphere as they arrive. Energetic neutral atoms are formed when fast solar wind ions encounter slow interstellar atoms. The solar particle captures an electron from the interstellar atom, becomes electrically neutral, and travels in a straight line unaffected by magnetic fields. like a bullet that suddenly becomes invisible to magnets mid-flight. These neutral atoms travel from the boundary regions back toward the inner solar system, where IBEX can detect them from Earth's orbit. By mapping where they come from and how energetic they are, IBEX can build a picture of the heliosphere's boundaries without ever leaving Earth's neighborhood. What IBEX found in its first maps published in 2009 was a feature that no model had predicted. A ribbon, a narrow, bright band of enhanced particle emission curving across the sky in a great arc, a region of the heliosphere boundary that was producing far more energetic neutral atoms than the surrounding areas. The ribbon did not follow the expected pattern of the heliosphere's boundary structure. It appeared to trace the direction of the local interstellar magnetic field, as though the magnetic field outside the heliosphere was compressing and shaping the boundary in ways that created a visible seam. Wait, the heliosphere had a seam, a structural feature, a visible, mappable line where the interstellar magnetic field was pressing hardest against the boundary of the Sun's domain. Here is where the science becomes genuinely unsettled, and where a legitimate, ongoing scientific disagreement reveals just how much remains unknown about the most fundamental structure in our solar neighborhood. For much of the late 20th century, the standard model of the heliosphere's shape was the comet model. The heliosphere was pictured as comet-shaped, rounded and compressed on the upstream side, facing the direction of the Sun's travel through the galaxy, and trailing a long tail on the downstream side, the way a comet's tail streams away from the Sun. This model made physical sense. The interstellar medium flows around the heliosphere like water around a moving boat, and the expected wake structure would create a long downstream tail. But here is where the shatter arrives. In 2015, a team of scientists led by Merav Ofer at Boston University published a paper in the journal Nature proposing a fundamentally different shape for the heliosphere. Not a comet with a long tail, but a shape more like a crescent or a croissant. In this model, the solar magnetic field, which at the Sun's poles is oriented differently than at the equator, deflects the solar wind outward in two distinct lobes rather than one continuous tail. The result is a heliosphere with a rounded upstream side, but two distinct downstream lobes where the solar wind flows preferentially outward, creating a structure that looks nothing like the comet model. Ofer's team supported their case with magnetohydrodynamic simulations, computational models of how plasma and magnetic fields interact across enormous scales. The crescent model fit certain observations that the comet model struggled to explain. Scientists on the other side of this debate were not persuaded. They pointed to observations from the Cassini mission, NASA's Saturn orbiter, which detected additional energetic neutral atoms from the heliosphere's boundary before its mission ended in 2017. That seemed more consistent with a longer downstream tail than the crescent model predicted. Both models have published support. Both have published critiques. The true shape of the heliosphere, one of the most fundamental facts about the structure of our solar system, remains as of today genuinely uncertain. The termination shock is asymmetrical, confirmed by direct measurement. The heliosheath is thinner in some directions than others, confirmed by Voyager 2. The IBEX ribbon revealed a structured, inhomogeneous boundary, confirmed by observation. Two competing shape models, crescent versus comet tail, both supported by real data. The heliosphere's shape is not a settled question. It is one of the most actively debated problems in heliospheric science. But here is why the shape of the heliosphere is not merely an aesthetic question or an academic one. The shape determines the shielding. A heliosphere compressed strongly on one side and thinner in certain directions does not protect every part of its interior equally. If the heliosphere has two distinct downstream lobes separated by a narrower region, the cosmic ray shielding in those narrower regions may be reduced relative to the more robustly protected inner solar system. The radiation environment inside an asymmetric heliosphere is itself asymmetric. and understanding that asymmetry matters for understanding the actual radiation history of the inner solar system and of Earth. Beyond that, the shape of the heliosphere determines how the Sun interacts with the interstellar medium as it moves through the galaxy, and the Sun does not always move through the same kind of interstellar environment. Over millions of years, the Sun passes through regions of the galaxy with different gas densities, different magnetic field strengths, different distributions of interstellar material. Each of those environments would interact differently with the heliosphere, compressing it in different ways, distorting it in different directions, potentially changing its shielding properties for Earth. Picture this. Imagine you are holding an umbrella in a wind that is gusting from different directions. The umbrella's protection is not equal in all directions, and if the wind shifts, the coverage shifts. The heliosphere is that umbrella, and the galaxy is the wind. Understanding the umbrella's true shape tells you something important about which directions the rain is getting through. The shape of the structure that protects you is not an abstraction. There are regions of the galaxy's interstellar space where the heliosphere, compressed by denser interstellar gas, would be smaller and would provide less shielding than it does today. The Sun has moved through such regions before. It will again. The cosmic ray history of Earth, the variations in radiation exposure that may have influenced mutation rates, climate, and the pace of biological evolution over hundreds of millions of years, is written in part in the shape of the heliosphere, as it was during each of those passages. Voyager's data is one of the primary tools scientists have for beginning to reconstruct that history. What Voyager's asymmetry measurements revealed, and what the ongoing scientific debate about the heliosphere's shape reflects, is that our solar system is not an island floating free in a featureless void. It is embedded in an environment. The interstellar medium presses against it. The galactic magnetic field shapes it. The direction of the Sun's motion through the galaxy compresses it from one side and stretches it from another. The heliosphere is not a simple sphere generated by a simple source. It is a complex, asymmetric, dynamically shaped structure, continuously negotiated between the Sun's outward pressure and the galaxy's inward one. And the complexity of that negotiation, the true shape of the bubble we live inside, is something we are still learning to see clearly, using data that a spacecraft launched nearly 50 years ago is still providing. That is the nature of Voyager's legacy, not a mission that closed questions, one that opened them with a precision and a depth that will take generations to fully exhaust. And now, the final discovery. Because Voyager 1 has not stopped. It has not slowed meaningfully. It is traveling outward through the local interstellar medium right now, measuring, transmitting, operating on power generated by the decay of radioactive plutonium in a generator that has been running since 1977. The distance it has reached and the measurements it is making there in the true ocean of interstellar space represent the 9th and final discovery of this journey. And in some ways it is the simplest discovery of all 9. Not because it is the least significant, because it is the most direct. For the first time in human history, we know what it is like out there. Not theorized, not modeled, measured. And the picture that Voyager has built, particle by particle and oscillation by oscillation, from inside the most remote environment any human instrument has ever inhabited, is the first true portrait of the interstellar ocean that our solar system is sailing through. That is shocking discovery number 9. Voyager 1 is falling, not toward anything, not because of gravity pulling it down, falling outward the way all things in space fall when nothing stops them, continuing the trajectory set 48 years ago by a rocket that has long since burned to nothing and tumbled back into the atmosphere. It is falling through the interstellar medium right now, at this moment as you watch this, at roughly 38,000 miles per hour, about 61,000 kilometers per hour, which sounds fast until you understand that at that speed, it would take Voyager approximately 73,000 years to reach the nearest star beyond our Sun. 73,000 years. The entirety of modern human civilization multiplied many times over to cross just one small step in the interstellar ocean, and yet Voyager is the farthest thing humanity has ever sent anywhere. And what it is measuring as it falls is something no instrument has ever measured before. This is shocking discovery number 9. Let us place ourselves precisely in space and time, because the numbers here deserve to be felt before we move past them. Voyager 1 is currently more than 15 billion miles, roughly 24 billion kilometers, from the Sun. That distance increases by approximately 38,000 miles, 61,000 kilometers, every hour. Every hour. While you were asleep last night, Voyager traveled roughly the distance from New York to Los Angeles and back again, nearly 8 times, and it did that every single hour, all night, without pause. Voyager 2, traveling in a different direction at a slightly slower speed, is currently more than 12 billion miles, roughly 20 billion kilometers, from the Sun. 2 spacecraft, 2 directions, 2 separate paths through the interstellar medium, both still transmitting, both still measuring, both still alive. Together, they constitute the entirety of humanity's direct presence in interstellar space. That is not a metaphor or a loose approximation. It is a precise and literal fact. Every other spacecraft ever launched is either destroyed, orbiting something in the solar system, or in transit within the heliosphere. Only Voyager 1 and Voyager 2 are beyond the heliopause. Only they are measuring the local interstellar medium from the inside. 2 machines the size of small cars, in an ocean with no shore in sight. Discovery number 9 is not a single event. The way the termination shock crossing, or the heliopause crossing, were single events with specific dates attached. It is an ongoing revelation, a continuous accumulation of direct measurements from the only instruments humanity has ever placed in interstellar space. And what those instruments have collectively built in the years since Voyager 1's crossing in 2012 is the first real portrait of the local interstellar medium as a physical environment. The plasma density measurement, established through the plasma wave instrument and the cosmic hum we explored, gave scientists the first in situ confirmation of the interstellar medium's electron density in our immediate cosmic neighborhood. The value confirmed theoretical predictions in its broad outline, while revealing specific details that required model refinements. The magnetic field measurements have been among the most scientifically rich returns from the interstellar phase. Voyager 1's magnetometer is measuring the direction and strength of the local interstellar magnetic field, the galaxy's own magnetic environment, distinct from the solar magnetic field that was carried outward through the heliosphere. The interstellar magnetic field is oriented differently from what many models predicted, tilted at an angle to the galactic plane that does not precisely match earlier estimates derived from indirect observations. This orientation affects how the interstellar medium flows around the heliosphere. It affects the heliosphere's shape. It has implications for every model of how our solar system interacts with the galaxy, and the galactic cosmic ray spectrum, the energy distribution of the particles streaming through the interstellar medium around Voyager, has provided the most complete direct measurement of the local interstellar radiation environment ever obtained. Every data point Voyager sends home from this measurement is irreplaceable. There is no other way to get it. No telescope can substitute for an instrument physically inside the environment it is measuring. To receive these measurements, mission controllers at NASA's Jet Propulsion Laboratory in Pasadena communicate with Voyager through the Deep Space Network, a system of enormous radio antenna dishes located at 3 sites distributed around Earth: California, Spain, and Australia. The 3 sites are positioned so that as the Earth rotates, at least one dish can always maintain contact with any spacecraft in the solar system and beyond. The dishes that communicate with Voyager are extraordinary instruments in their own right. The largest among them span up to 230 feet, about 70 meters, in diameter. 230 feet is roughly the height of a 20-story building, laid on its side as a curved metal surface, aimed with extraordinary precision at a point in the sky where Voyager is calculated to be. And the signal they receive from Voyager is almost unimaginably faint. Voyager's transmitter produces 23 watts of power, less than a typical household LED light bulb. That signal travels more than 15 billion miles, spreading outward as it goes, weakening with the square of the distance until it arrives at Earth so attenuated that the power reaching the antenna is measured in femtowatts, quadrillionths of a watt. The signal is so weak that the dish's own electronics must be cooled to near absolute zero, near -4, 160 degrees Fahrenheit, or -273 degrees Celsius, to reduce electronic noise enough to hear it at all. And despite all of that, despite the distance, despite the whisper-thin signal, despite the 48 years of travel, the Deep Space Network is still hearing Voyager, every day, still listening. Picture this. You send a letter to a friend. The letter travels at the speed of light, the fastest speed the universe permits. It takes more than 23 hours to arrive. Your friend reads it, writes back immediately, and sends the reply at the speed of light. The reply takes more than 23 hours to return. You sent your letter, and you will not read the response for nearly 2 days, at the speed of light. That is what it means to communicate with Voyager 1 today. Every command sent from JPL waits more than 23 hours before it reaches the spacecraft. Every piece of data Voyager transmits has been traveling through space for more than 23 hours before it arrives at a dish in California or Spain or Australia. The scientists who work on this mission are in constant dialogue with a machine that is answering questions asked yesterday, in a conversation that moves at the pace not of human exchange but of light crossing an ocean of space. And yet they carry on that conversation every day, because every day the data that comes back is data that exists nowhere else in the universe, data that no other instrument positioned anywhere on Earth or in orbit can obtain. The conversation is slow, and the distance is almost beyond comprehension, and the machine is aging, but it is still talking, and the scientists are still listening. This is the part of the story that carries weight in a different register than the physics and the discoveries, because Voyager is not permanent, it is running down. Voyager 1 and Voyager 2 are powered by radioisotope thermoelectric generators, instruments that convert the heat released by the natural radioactive decay of plutonium-238 into electricity. There is no fuel to run out, there is no combustion to sustain, just the slow, predictable decay of radioactive atoms, releasing heat, which is converted to electricity by thermoelectric elements, which power the instruments. Plutonium-238 has a half-life of approximately 87.7 years, meaning that every 87.7 years, half of the remaining plutonium decays away, and the power output of the generator falls accordingly. The generators were producing roughly 470 watts of electricity at launch in 1977. By now, they are producing significantly less, around half of the original output. The power available to run Voyager's instruments has been declining by roughly 4 watts per year, roughly the power of a small nightlight every year since launch. To manage this slow decline, mission engineers have been systematically shutting off instruments and heaters. The cameras were turned off years ago, they required too much power, and there was nothing in the featureless dark to photograph anyway. Other instruments have been powered down one by one as the energy budget has tightened. Each shutdown is a small ending, a piece of the mission going permanently dark, never to return. NASA estimates that the spacecraft will be able to power at least some science instruments through approximately the late 2020s. Beyond that, the power will likely drop below the threshold needed to operate any instrument or transmit data home. The signal will weaken, the telemetry will stop, and Voyager will continue traveling outward, silent, indefinitely, a message in a bottle thrown into an ocean so vast that the bottle will drift for millions of years before anything encounters it. 23 watts of power, less than a household. Light bulb, a signal arriving 23 hours after it was sent. Instruments shutting down one by one as the power fades. Still measuring, still transmitting, still discovering, nearly 50 years after a 5-year mission was supposed to end. The engineers who built Voyager expected to retire before the mission concluded. Some of them did. Some of them have died. The scientists who have spent their careers analyzing Voyager's data, who have given decades of their professional lives to a machine they will never see, communicating across distances that light takes a day to cross, a part of the longest sustained human scientific endeavor in the history of space exploration. When Voyager finally goes silent, it will take something irreplaceable with it. Not just the instruments, the relationship, the daily act of listening to a machine so far away that the listening itself is a statement about what human curiosity is capable of. You are alive during the years when that conversation is still happening, right now, today. We have traveled a long way together through this story, from a launch pad in Florida in 1977, through the gravity-slung arcs past Jupiter and Saturn, outward through decades of silence and solar wind, across the termination shock and through the storm of the Helios sheath, past the stagnation region and through the heliopause, and now here, in the interstellar ocean, where a machine built in the age of typewriters and rotary telephones is floating in the space between the stars, measuring the universe and sending us postcards. It is worth pausing for a moment to simply sit with that. Not the data, not the physics, just the fact of it. We built something small and fragile and filled it with curiosity, and we threw it as hard as we could into the dark. And it went, and it kept going. And it is still going now, right now, in the direction of the constellation Ophiuchus, the serpent bearer, carrying with it the signal of everything that wanted to reach beyond what we could see. That is a remarkable thing for a species to have done. What Voyager has established in the interstellar medium is not a completed picture. It is a first sketch, extraordinarily valuable precisely because it is the first, and because no second sketch yet exists. The plasma density, the magnetic field orientation, the cosmic ray spectrum, the plasma wave activity, all of it is the beginning of a scientific understanding that will take generations to fully develop. Future missions will be needed. Missions that travel faster, that carry more sensitive instruments, that follow Voyager's path into the interstellar medium with the benefit of everything Voyager taught us about what to expect. Those missions do not yet exist. They have not yet been built or launched. The designs are sketched in proposals, not metal. When they fly, if they fly within the lifetimes of people alive today, they will go into a region that Voyager has already mapped in outline. They will be following a path that 2 machines launched 48 years ago on a 5-year mission already walked. Voyager will not be there to greet them. It will be millions of miles farther out by then, still moving, still falling through the dark. But the data will still be here, on servers and hard drives, and in the memories of the scientists who spent their careers listening. Everything Voyager found, every number, every measurement, every discovery, preserved, waiting for whatever humanity builds next to carry it forward. But there is one more thing to say about this mission, one final dimension that the science alone cannot fully capture. Because Voyager is not just a science mission, it never was. On board each spacecraft, attached to the bus that carries the instruments and the transmitter and the nuclear generator, there is a 12-inch gold-plated copper disc, a record, encoded on it, the sounds of Earth, the sight of Earth, the greetings of Earth in 55 languages, the music of Earth, from Bach to Chuck Berry, from Navajo night chant to Azerbaijani bagpipes, a message from a species that looked out into the dark and decided it was worth trying to say hello. The golden record is not a scientific instrument. It produces no data. It measures nothing. It will never transmit home. But it is traveling through the interstellar medium right now. Past the plasma Voyager has measured, through the cosmic rays that flood the space beyond our heliosphere, past the hum of the interstellar gas, outward indefinitely in the direction of the stars. What that means, what we were really saying when we put it there, is the final thing this story has to tell. There is a record on board, a physical record, 12 inches across, gold-plated copper, encoded with sounds and images selected by a small committee of human beings in the spring and summer of 1977. Carl Sagan chaired that committee. He and his colleagues worked against a deadline. The launch windows were fixed by the planet's positions, not by human preference. And in the months before Voyager left Earth, they assembled something that had never been assembled before in the history of our species. A message. Not a message to anyone in particular. A message to whoever, or whatever, might someday find it. It is on board both spacecraft right now, traveling through the interstellar medium, coated in gold to resist corrosion across timescales that make the entire history of human civilization look like an afternoon. Enclosed in an aluminum case, engraved with instructions in the language of mathematics and physics, the only universal language anyone could think of for how to play it. Voyager was always more than a science mission. It was an act of reaching. Let us take a full measure of where we are and how far we have come, not just in this story, but in the physical reality of the mission itself. Voyager 1 is traveling in the direction of the constellation Ophiuchus, the Serpent Bearer, at roughly 38,000 miles per hour, or 61,000 kilometers per hour. At that speed, it will take approximately 40,000 years for Voyager 1 to pass within roughly 1.6 light-years. That's nearly 10 trillion miles of the star Gliese 445. That is not a destination. Voyager is not aimed at any star. It is simply traveling in the direction it was sent, and stars are so far apart that even on a 40,000-year timescale, a close approach to any of them is more coincidence than trajectory. The nearest star to our Sun, Proxima Centauri, is approximately 4.2 light-years away. That is roughly 25 trillion miles, 25 million miles. Voyager 1, traveling at its current speed, would take approximately 73,000 years to cover that distance. 73,000 years ago, our species was anatomically modern, but had not yet crossed into the Americas, had not yet developed agriculture, had not yet written a single word. The entire recorded span of human civilization, every empire, every discovery, every library ever built, fits inside a fraction of the time it would take Voyager to reach the nearest star. And yet, it is going. Not because it will arrive, but because we sent it. The golden record carries 115 images encoded as audio signals. Images of Earth, of life, of human bodies, of landscapes, of cities, of scientific diagrams. It carries greetings in 55 human languages, from Akkadian, one of the oldest written languages ever spoken, to Wu Chinese. It carries the brainwaves of Andruyan, who was thinking about the history of the world and the experience of falling in love as the recording was made, and whose neural patterns, the electrical signature of a human mind in the act of feeling, are encoded in the grooves alongside the mathematics and the music. It carries 55 minutes of music from around the world. Johann Sebastian Bach's Brandenburg Concerto No. 2 in F major. Complex, ordered, mathematically elegant, full of the human voice of the 18th century. Blind Willie Johnson's Dark Was the Night, Cold Was the Ground. A wordless, aching slide guitar performance from 1927, described by Carl Sagan as the loneliest sound ever recorded, a sound that emerged from one man's private grief and now travels through interstellar space. A Navajo night chant, a Peruvian wedding song, a pygmy girl's initiation song from Zaire. The sound of Chuck Berry's Johnny B. Good, electric and exuberant and entirely human. It carries the sound of a human heartbeat, the sound of rain and surf and wind, the sound of a cricket, the sound of a mother's first words to her newborn child. Picture this, somewhere in the Milky Way, many millions of years from now, something finds Voyager drifting in the dark. It has been travelling for so long that the sun has aged measurably. The planets have shifted in their orbits. The continents of Earth, if Earth still exists, have moved. And this thing, this intelligence, if it is intelligent, this curiosity, if it is capable of curiosity, reaches out and takes the record from its case. And somewhere on whatever serves it for hands, it presses play. And it hears a heartbeat. In the 4.5 decades since Voyager 1 became the first human-made object to leave the solar system, the data it has returned has transformed our understanding of the structure we live inside. We know now that the heliosphere is real, not merely theorized, but measured directly from the inside by instruments that crossed its interior over 35 years. We know its inner regions, its turbulent middle zone, its structured outer boundary. We know where the termination shock sits, and we know it sits in different places in different directions, because the heliosphere is not a sphere, but a dynamic, asymmetric structure shaped by the galaxy pressing against it from outside. We know the Helios heath is not a gentle transition, but a storm zone of chaotic magnetic fields and trapped energetic particles, an environment far more active and far more complex than any model prepared us for. We know the stagnation region exists, that final zone where the sun's own wind gives out and turns back before the boundary is reached, a phenomenon no theory had included. We know the heliopause is real and measurable and sharp, crossed by Voyager 1 on August 25, 2012, and confirmed by Voyager 2 on November 5, 2018. 2 crossings, 2 directions, 1 boundary, verified. We know the galactic cosmic ray environment beyond the heliopause is significantly more intense than inside it, a difference that matters for the biology of every living thing in the solar system and for the engineering of every future human mission beyond it. We know the interstellar medium hums, not metaphorically but physically, in a persistent plasma oscillation that carries direct information about the density of the space between the stars. And we know that the shape of the heliosphere, the structure that has protected life on Earth for 4.5 billion years, is still, in its finest details, a genuinely open question. 9 discoveries, each one the result of a mission that was supposed to last 5 years, and has now lasted nearly 50. Each one produced by instruments that have been travelling since the year that the first Star Wars film was released in cinemas, that predated the personal computer, that were designed by people using slide rules and hand calculations. You are the inheritor of all of this. Every measurement Voyager has made, every particle count, every magnetic field reading, every plasma oscillation detected in the dark beyond the heliopause is knowledge that belongs to you as surely as it belongs to the scientists who extracted it from the telemetry. You understand, having travelled this far through this story, something that the vast majority of people alive on Earth today do not understand in this depth. What the solar system's boundary is, how it was found, what it looks like from the inside, and what lies beyond it. That is not a small thing. That is exactly what Voyager was built to produce. Not just data, understanding, yours and ours, and everyone who wants it. Proxima Centauri is 4.2 light-years away. That is the distance that light, the fastest thing in the universe, at 186,000 miles per second, travels in 4.2 years. 4.2 years of light. That single step, the distance to the nearest star beyond our Sun, is a distance so staggering that Voyager, travelling at a speed no rocket in history has exceeded, would require 73,000 years to cover it. In the entire history of our genus, Homo in all its forms across roughly 2.5 million years of existence, we have not had time to cross the distance to the nearest star, even if we had started at the beginning of our species, travelling at Voyager's speed. The galaxy is not a place we will explore quickly. The stars are not neighbours in any ordinary sense of the word. The interstellar ocean is not a body of water that human civilization will sail across in any time frame that resembles the arc of history we know. And Voyager, our one and only ambassador in that ocean, crossed the heliopause at 121 astronomical units from the Sun. That is 11.2 billion miles. The nearest star is 25 trillion miles away. Voyager has covered roughly 0.06% of the distance to the nearest star. 0.06%. That is how far we have reached. That is also how far we have reached. The first step. The only step so far. But a step that no species, as far as we know, in the entire 4 billion year history of life on this planet, or perhaps in the history of any life, anywhere, had ever taken before. A 5-year mission that became a 50-year mission. 9 discoveries that rewrote the science of the heliosphere. 2 spacecraft in interstellar space, the only ones in human history. A golden record travelling outward through the dark, indefinitely, still transmitting. In the beginning of this story, that phrase meant something functional. Still transmitting, as in the machine still works. The signal still arrives. The instruments are still powered. The conversation across billions of miles is still ongoing. But after everything we have followed together, across the termination shock and through the heliosheath storm, past the stagnation region and through the heliopause into the interstellar medium, through the cosmic hum and the particle rain and the asymmetric shape of the bubble we call home, that phrase means something different now. Still transmitting is not about the machine anymore. It is about the act itself, the decision made in 1977 by a group of human beings who built something extraordinary and then refused to stop listening to it, to keep reaching, to keep measuring, to keep sending the data home and keep receiving it and keep building understanding from it. One photon at a time, across a distance that light takes more than 23 hours to cross. That act of refusing to stop listening is itself a discovery. It is what the mission revealed about the species that built it. We are the kind of creature that does not stop. Voyager 1 is the most distant human-made object in existence. There is nothing else out there, no other machine, no other signal, no other evidence of our presence, beyond where it has travelled. Everything we have ever built, every satellite and space station and planetary probe, every spacecraft launched in the history of our civilization exists within the heliosphere. Within the bubble, within home. Only Voyager has crossed the line. The nearest star waits at a distance that makes Voyager's position feel like the first step outside a front door. The galaxy beyond that, 200 billion stars, 100,000 light-years across, is a territory so vast that even imagining it at human scale produces only silence and a particular quality of stillness. We have not begun to cross it. We do not yet have the tools to begin to cross it. The future that holds such crossings, if it exists, belongs to descendants who have not been born, living in a civilization we cannot envision. But something made by human hands is out there, moving, in the dark between the stars, beyond the reach of the sun that made us, beyond the boundary that has sheltered life on Earth since the first cell divided in the first warm water 4 billion years ago. Something we built is travelling outward, carrying our heartbeat, carrying our music, carrying 48 years of measurements sent home faithfully across distances that the word vast cannot begin to hold. Contact will end, the power will fall below the threshold, the signal will cease, and Voyager will continue, silent, intact, indefinitely outward, a message that asked nothing of the universe except to be received. We do not know if it ever will be, but we sent it anyway. And in a universe this old, in a galaxy this wide, in a cosmos this indifferent to the small, bright fact of our existence, the sending of it was already in itself one of the most extraordinary things we have ever done. In the cold, silent vastness of the interstellar ocean, the Voyagers carry more than just instruments. They carry our curiosity, our music, and our greetings to a future we will never see. Long after the last star in our sky has faded and the Earth itself is a memory, these two small vessels will still be out there, drifting through the dark, the only remaining evidence that once, on a pale blue dot, there was a civilization that dared to reach for the edge of forever.